At its birth 4.5 billion years ago, the Earth is a gigantic ball of fire. Then it cools, making way for the appearance of the first oceans and the first embryos of continents. In the course of time, these emerging lands moved closer to one another. The oceans that separated them disappeared into the depths of the Earth's mantle. This phenomenon generated colossal forces. Under the surface, the temperature and pressure shot up like an arrow. In these extreme conditions, carbon crystallized in certain areas and was transformed into diamond. In South Africa, geologist Steve Richardson takes a great interest in these diamonds, a precious legacy of those past collisions. His research zone is located in Kimberley, in the province of Northern Cape, South Africa. On this site, we find what is called a craton, a zone which has not undergone any major change for several million or billion years. The Kimberley region is one of the oldest lands in all of Africa. And most importantly, it's precisely in this area that during our planet's infancy, two fragments of the Earth's crust collided.
This is a glacial pavement in the heart of the Karpval Craton. Deeper down, underlying the lavas, are even older granites that were produced by vertical differentiation of even earlier volcanic plateaus, which ultimately led to the production of granites and the formation of early Archean continental nuclei, which bobbed around on the Earth's surface by largely vertical movements. It was only when the Earth's crust had cooled sufficiently to make the crust more rigid that horizontal tectonics could take over. We have here in the Karpval Craton the first good evidence of the onset of plate tectonics, when the Kimberley block and the Witwatersrand block collided at some 2.9 billion years ago.
2.9 billion years, the estimated age of the first lands of the African continent. A number that Steve and his colleagues try to confirm with the help of diamonds present in the subsoil. These mythic precious gems brought fortune to Kimberley in the late 19th century. The story begins in 1867. A young farmer discovers a strange rock on a hillside. It is in fact the first diamond ever unearthed on South African soil. Baptized Eureka, it forever marked the history of the country. For years, prospectors from all over the globe set up shop in the region and dig the soil in search of riches. Today, a vast gaping hole attests to that scramble of olden days. Big Hole, 500 meters in diameter, the largest hole ever dug entirely by human labor.
This mine was started in 1871, and it took some 12 years for them to dig this hole down to a depth of around 200 meters. And it was a rich diamond pipe, and so the grade of diamonds and the quality of diamonds was very good, and so they decided that they needed to dig a shaft underground to further exploit those diamonds. As the hole deepened, it started to reveal the deep origin of diamonds, which until then was not understood. Prior to that time, diamonds were found mostly in alluvial workings. Here, as the hole went down, it went through the layers of geology and started revealing the outlines of a volcanic pipe, which comes ultimately from some depth of 100 to 200 kilometers down. And so this hole eventually was recognized as a volcanic pipe, which would have been erupted some 90 million years ago and breached the surface, which at that time was some 1 kilometer above where we are now.
The discovery of a volcanic pipe on the mine site gave scientists a unique opportunity to dive into the bowel of the Earth thanks to diamonds. These precious stones formed 100 kilometers underground. Much later, a volcano was born on this exact same site. The gemstones were thus pushed up, transported by a lava with a distinct makeup called kimberlite. Erosion then did its part, and over the course of centuries, the volcano disappeared completely. The diamonds are thus invaluable witnesses to past geological phenomena. Knowing their age means knowing the age of the rocks they were born from, the latter being inaccessible as they are buried in the depths of the Earth. Only a few rare specimens have been gathered from the volcanic pipe. They are carefully preserved here at the Big Hole Mine.
These are slices of the two main mantle rock types, eclogite and peridotite. They're very different compositions. If we look closely, in the eclogite, the garnets are a beautiful orange color, whereas in the peridotite, they're a purple color. And the reason why the peridotite garnets are so purple is that these are residual compositions from the removal of a melt that allowed for the stabilization of the carp-foil craton keel. Now, it's these mantle rocks that have been carried from a depth of 150 to 200 kilometers that are the host rocks in which diamonds form. So we can talk about peridotic diamonds and eclogitic diamonds. And it's the disaggregation of these rocks that allows for the diamonds to be found in the kimberlite at the surface. And here I have a specimen of a diamond, an octahedral crystal of diamond, lodged in a piece of the original kimberlite magma from this volcanic pipe. Some of these diamonds have inclusions of garnet, either an orange garnet or a purple garnet inside the diamond. So the kimberlite is simply the train that has brought the diamonds to the surface as accidental passengers after they were disaggregated out of their mantle host rocks, the peridotite and the eclogite.
It's at the University of Cape Town in the Geological Sciences Department that Steve Richardson studies these diamonds in an effort to date them. The stones that interest the geologist are not the most precious. On the contrary, he only analyzes those that contain impurities. Infinitesimal slivers of rock inherited during their formation.
My ultimate aim is to date these diamonds based on the mineral inclusions that I'm looking for in these diamonds. It turns out that you can't date the diamonds directly, for example, by the carbon-14 dating technique, because that technique only applies to the last 50,000 years or so. Whereas we're talking about diamonds that are around 3 billion years in age. So I'm looking for mineral inclusions in these diamonds, particularly garnet, which I can identify on the basis of color as being from either eclogite, where the garnet is orange in color, or peridotite, where the garnet is purple in color. Once I've made those identifications, I'm then going to proceed to crack the diamonds to release the inclusions, which I will then dissolve to extract the trace elements that we use for dating prior to introducing the samples into the mass spectrometer.
Steve and his team have already studied more than 3,000 diamonds. For the moment, all the analyses concur. The stones are 2.9 billion years old. The Kimberley region does indeed lie on one of the oldest of African lands, the skeleton of the future continent. After it was formed, this first African territory grew little by little. Other islets of the Earth's crust collided with the craton and joined to one another over millions of years. But 2 billion years ago, a sudden and tremendous impact jolted the entire region. It took place in South Africa, where the little town of Redfort is today located. Here, the landscape looks as though it's been tousled by the hands of a giant. Geologist Roger Hart has studied these rocks for years, decrypting the clues of the ancient disaster.
The rocks here are granites. This is a rock that is common throughout the world. But here at Vredefort, there's another component that indicates to us that something catastrophic has happened here. What we see here are these black veins and rounded boulders of granite, which are known as pseudotachyllite breccias. The composition of the pseudotachyllite is exactly the same as the granite. What we now believe is that the pseudotachyllite and the breccias were formed through heat and friction. These pseudotachyllite breccias are generally regarded as indicative of impact processes and are found at most craters worldwide. But here at Vredefort, they are particularly well developed, suggesting to us that Vredefort is a particularly large and violent impact.
Such a violent impact could only be caused by an object fallen from space. A gigantic meteorite, more than 10 kilometers in diameter.
What happens when a meteorite this size strikes the Earth? Well, firstly, you form a big hole. Secondly, this is immediately followed by rebound and uplift in the center of the crater, much like when you throw a stone into a pond of water and you get the central uplift. So if the crater here was 30 kilometers deep, you have a central uplift of about 30 kilometers. What happens to the meteorite? Well, it generally vaporizes, especially in a crater of this size and with this amount of energy. How big are they? What kind of explosion do they form? Well, in general, if you took all the world's nuclear arsenals and put them together, that doesn't even begin to compare with the explosion that formed at the time of Vredefort.
The meteorite burrowed a crater more than 300 kilometers wide and 30 kilometers deep. It's one of the largest and oldest craters on the planet. A lesion left by one of the most devastating disasters in Earth's history, the crater gives scientists unique access to the geological structure of the subsoil.
The rocks that we see here are sediments, quartzites to be exact. Quartzites like this are common throughout the world. In the normal sense, sediments and quartzites generally form in layers, horizontal layers. Normally these sediments rest on basement rocks, such as granites, and the granites normally rest on mantle. But not here at Vredefort. These are quartzites that have been turned vertical. In fact, what some of us believe is an entire 36-kilometer sequence of rocks has been turned on edge, exposing a vast section of the Earth's crust to view. Now, what is interesting for scientists is that this section gives us the opportunity to study the Earth's crust through geological time. What we believe is that these quartzites overlie granites, and that in the very center of Fredefort, we possibly have mantle rocks exposed. So we're talking a sequence in time going back to almost 3.6 billion years, the age of the rocks in the center. This is a very interesting concept for geologists because it allows us to study the chemistry, the tectonics, and the evolution of this crustal section in time and in space.
A veritable paradise for geologists, the Vredefort crater is a place unlike any other on Earth. Here, scientists have access to 3 billion years of evolution on a single outcrop. They can thus better comprehend the structure of the rocks that make up our planet. Roger has dedicated his career to the study of this meteorite. Even though it's not strictly speaking a tectonic phenomenon, its impact had the same effect. It transformed the face of the entire region.
Mountains can be formed in many ways. We know that mountains can be formed, for example, like the Alps, through tectonic processes. We know that volcanoes form mountains, like Vesuvius, but not here. These mountains are formed by meteorite impact. Meteorites are visitors from outer space. They are pieces of rock that are moving through our solar system and randomly impact anything that gets in the way. For example, you look at the moon is covered by meteorite impact craters. On Earth, we don't have that many. The reason you don't get that many craters on Earth is the Earth, unlike the other planets, which are dead, Earth is dynamic. Earth is living. Earth has plate tectonics. Plate tectonics destroys craters. Earth has erosion. Earth has water. The important point here, Earth is a dynamic, living planet.
Following this dramatic encounter with an object fallen from space, Africa experienced other upheavals. The land masses of the southern hemisphere continued to converge until nearly 800 million years ago they at last formed a supercontinent, Gondwana. Even today, the landscape tells the story of Gondwana's birth, a major episode in Africa's history. The Fish River Canyon is located in Namibia. At 160 kilometers long and 27 kilometers wide in certain parts, it is by far the largest canyon on the continent. This sumptuous scenery is one of French scientist Olivier Dutoit's work sites. This researcher's goal is to retrace the geological history of the region in its smallest detail.
We're here before a magnificent landscape that was sculpted by the Fish River, there on the valley floor. This river dug through a series of rocks, making it possible to now study their history, and also creating this magnificent scenery. This history begins about 1 billion years ago. So what are we looking at? At the bottom of Fish River, near the valley, we see layers that incline, like this. Those are rocks that have been deformed, metamorphosed, and heated. They formed during a collision which produced a mountain range. So imagine above us was a huge mountain range with very high peaks, several thousands of meters of altitude, like, for example, the Alps or the Himalayas. And it was those rocks that made up the continent we call Gondwana.
When they collided, the rocks of the former African and American continents crumpled to the point of forming a gigantic mountain chain. Water and wind then eroded the rock. Several tens of millions of years later, the mountain peaks disappeared, and the sea pushed into this area. Thus began a long phase of deposits on the seabed. Sediments formed successive even layers of strata. But a little more than 500 million years ago, a new tectonic thrust progressively pushed up the ground in the region. The sea then receded, revealing the multi-layered geological strata that the river would cut through bit by bit.
What we also see clearly are these horizontal layers, which means that for about 500 million years, nothing has happened in this region.
From the canyon's ridge, Olivier Dutoit can thus contemplate 1 billion years of West African history. At the deepest levels are vestiges of the collision of the continental plates during Gondwana's formation. Above, hundreds of strata are stacked up, revealing almost imperceptible variations. Tirelessly, the scientist crisscrosses the area and gathers a multitude of specimens from the rocks. Their analysis will one day make it possible to describe the infinitesimal movements that stirred the region until the present day.
It's interesting to understand why, in a zone that is known to be stable, we find quantifiable vertical movement, even if it's minimal. It's moved about 1,400 meters in 500 million years, enough to mold the entire landscape we see in Africa today.
The Fish River region is one of Africa's best to tell the story of the ongoing voyage of the continents. 700 million years ago, it was here that the future South American plate collided with Africa. During the same period, another phenomenon was taking place further north. A small fragment of land also collided with Gondwana. Traces of this event can still be found today in the Sultanate of Oman on the Arabian Peninsula. Sonia Roos and Melina Macouin are geologists at the Institute for Research Development in southwestern France. Their mission: gather the proof of this ancestral collision that dates back 700 million years. Their research zone is located on the coast of the Arabian Sea. In the heart of these desert landscapes, they seek out veins of a specific type of igneous rock called dikes.
Oh, look, you can see it there. Yes. Crops out nicely. So we stopped here to look at this large dike, which is actually an igneous intrusion that comes from the Earth's mantle. Magma from the depths moved through the crust and changed composition as it crossed through the Earth's crust, forming a vertical intrusion that appears on the surface.
In building this road, bulldozers exposed several dikes. But they also changed their structure. This forces the geologists to find another site to collect samples from. These veins of igneous rock formed 700 million years ago during the violent collisions of the tectonic plates. Inside these rocks, minuscule crystals containing iron can be found. It's precisely this metal that is of interest to the scientists. The Earth is in fact surrounded by a powerful magnetic field. Its inclination varies at every point on the globe. When the dikes were formed, the iron they contained literally became magnetized. The crystals were thus oriented precisely to the Earth's magnetic field at that time. The rocks then moved around the planet's surface as the tectonic plates moved. But the crystals in the dikes remained frozen in their original position. In this way, they memorized, as it were, the localization of the rock, and thus the continent, at the moment of its formation. We call this paleomagnetism. To determine the ancestral position of this region, the scientists gather numerous samples along the coast.
So in the lab, we'll measure the paleomagnetic direction, which will give us an inclination, and we'll convert that into latitude. So we'll know at what latitude these dikes were formed. So 340? And 8.5. Our hope is that the samples collected during this mission will give us a position for time t. So not the whole story, but just the date of the intrusion of these dikes, somewhere around 700 million years ago.
Sonia and Melina carefully note the GPS position and, most importantly, the inclination of each specimen gathered. In the laboratory, the rock fragments are placed in a room that is perfectly insulated from exterior magnetism. An instrument then measures the orientation of the crystals inside the rock. Preliminary results seem irrefutable. 700 million years ago, when the dikes were formed, Oman was located at a latitude of 30 degrees south. This region thus was undoubtedly part of Gondwana. With the arrival of the future Arabia, all the pieces of the African puzzle began to come together. But in the southern region of the continent, near Cape Town, there's another event in the works. In the heart of the Cape Peninsula, the Table Mountain is the most famous vestige of a bygone collision. The plate that will later become Latin America enters into contact with West Africa. But in pivoting on its axis, it also butts up against South Africa. For John Compton, researcher at the University of Cape Town, this area is like home. He's roamed the cliffs of this massif for many years in search of new clues to the history of its formation.
Table Mountain is one of a much larger mountain chain. And this larger mountain chain formed at the time when Gondwana was forming. So from the west, we had South America, the continent, colliding with Africa. This produced large compressional forces of the collision of the two continents. So in that situation, when two continents collide, you have tremendous physical force of the two continents, and those tend to crumple and thicken the crust.
When the two continents moved closer together, the oceanic plate that separated them dove into the depths. Then the ocean disappeared, and the land masses were left face to face. They collided, and then continued to press against one another to the point of deformation. Between the two plates, gigantic reliefs then appeared. In the depths, granitic magma formed.
So the Cape Full Belt Mountains, of which Table Mountain is a part, formed from those collisions. So the northern branch to the north of us formed from when South America collided with Africa. The branch that goes to the east of Port Elizabeth formed when Antarctica collided from the south. So these two large continents joined Africa, and in that formation, all these rocks were crumpled up and formed into this folded mountain belt.
The Cape Fold Mountains run the entire length of the South African peninsula. They thus demarcate the zone where the continental plates collided. In the foothills, the violent collisions left other traces. Under pressure, the Earth's crust tore apart in several areas, allowing magma to rise to the surface. As it cooled, this magma turned into granite, a rock that is found all over the coast nowadays.
Behind me we can see Lion's Head, a famous monument in the Cape Town, where you can see the slopes of granite, and that same granite rock is exposed here along the coast. And this granite extends from here all the way south beyond Cape Point. It's a very large body, a large pluton of granite that's been emplaced here. You can tell it because it's very light in color. It has these very nice large crystals of feldspar in it that make it light in color, and it has intruded into this darker rock that I'm walking over now. And this darker rock is known as the Malmesbury group and was here before the granite intruded into it. So we can see this mixture of the contact zone between the granite rock to the south and this Malmesbury rock to the north. So I'm standing on part of that contact zone here, which includes this light-colored, large feldspar crystal granite and these ribbons of dark shale from the Malmesbury. So this sea point contact then is famous as both an example of deep Earth processes. This is probably was happening at about 5 kilometers below the Earth's surface at the time. It has since been exposed here through the long process of weathering and erosion, and we now see it at the surface. So what happened here was that approximately 540 million years ago, this granite got intruded into and placed into the Malmesbury. And the reason that happened was because at that time there was no Atlantic Ocean here, but there was an ocean like the Atlantic called the Adamastor Ocean. And instead of spreading apart as the Atlantic is today, the Adamastor Ocean was closing. So what was happening was the oceanic crust was getting subducted beneath the African continent. And what we see here is sort of a freeze frame image of that intrusion of that molten rock into the solid existing Malmesbury rock. That meant that we had the closing of the Adamastor Ocean, and the continents were then joined together to make for a larger supercontinent, Gondwana.
"500 million years ago, the formation of Gondwana was complete. All the continental plates of the southern hemisphere were pressed up one against another. As for the future African continent, it could be found at the center of this supercontinent.
If we look to the west, we have the Atlantic Ocean Basin, very large ocean basin that has formed over those past 130 million years. At that time, South America, Argentina, Buenos Aires, was right next door to us here in Cape Town. And to the south, we have Antarctica, and then further to the east, we have Australia, Madagascar, and India. And all those continents once used to all be together as well as part of Gondwana.
even after the birth of the supercontinent, tectonic movement didn't stop. Slowly, Gondwana drifted across the surface of the globe. Thus, the tip of the African plate found itself at the South Pole. The Earth entered into a phase of climatic cooling, and a large portion of Gondwana was covered in a thick layer of ice. In the Damaraland region of Namibia, this period of glaciation left traces even in the heart of the savanna. Several years ago, Nicole Ulrich discovered astonishing fossils here. Hundreds of petrified trees, perfectly preserved for millions of years.
Oh, this is fascinating. Look here. It looks like a piece of wood, but it's actually a big piece of rock. It's the rock because of the process of petrification. These trees once grew in a cold environment nearly 300 million years ago. They were uprooted, maybe by water, by a big flood, and they were very quickly covered by a lot of sediments. And by this process, they were cut off from oxygen, and therefore they could not rot. And over geological time, in a very slow process, the wood material was replaced by quartz that crystallized in the sediments. This area here is regarded as the largest assembly of fossilized wood in southern Africa. If you look at this example, it's a perfect example. The structure here looks like a bark from a present-day tree. All the fine lines are very well preserved. This is absolutely amazing.
In analyzing these petrified trees, specialists noticed they were species typically found in Nordic countries. When they grew here, this area resembled parts of Canada. The climate was cold and humid, a far cry from Africa today. These fossils are thus irrefutable proof that 300 million years ago, Gondwana was located at the level of the South Pole. But sometime later, the supercontinent once again moved north. It's the end of the Ice Age. Temperatures rise, the ice melts, and enormous quantities of water sweep through the entire region.
Here we have three examples of big fossilized trees. These trees are all situated more or less parallel to each other. This means that they will have been transported by river in an old river channel. Also, the sediments around here that we can find indicate river sediments. These trees give even evidence of plate tectonic movements. 270 million years ago in Namibia, they were growing in cold climate, which indicates that the whole continent was situated further to the South Pole. Then, due to plate tectonics, the continents have moved away from the South Pole and from the Arctic climatic conditions, and today we have hot desert conditions in Namibia.
Today, these trees frozen for eternity tell us of Gondwana's voyage across the surface of the globe, and most importantly, of the intense climate changes the region encountered in the past. But the era when Africa is the center of the world comes to an end. Tectonic forces tirelessly continue to mold the face of our planet. After millions of years of living as a unit, the continents go their separate ways. Each one evolves in an entirely different fashion from the others. India will collide with Asia and thus create the Himalayas, the highest mountain range in the world. Australia will become its own unique ecosystem, an island continent isolated from the rest of the globe. Antarctica wanders to the South Pole and transforms into a frozen territory. South America veers west, becoming home to the longest mountain range, the densest forest, and the mightiest river on the entire planet. Less spectacularly, Madagascar moves barely 400 kilometers off the African coast. But over the course of centuries, the Great Red Island evolves into a distinct and unique world all its own. In the northwest of the country, in Majanga, a young researcher is studying the exact phase when Madagascar separated from Africa. Karen Sammons is a biologist at Northern Illinois University in the United States. For more than 10 years, she's traveled here every summer to study fauna in this region. Her goal: learn how and during which period animal species arrived on the island. In the field, her team methodically excavates the soil in search of fossils and tiny clues buried in the ground, which recount in detail Madagascar's history.
So Madagascar was part of Gondwana, so 200 million years ago it was connected to the rest of the land masses. And it was actually between Africa on one side and India, so it was wedged between the two. And about 165 million years ago is when it actually separated from Africa. So even though we think of Madagascar as being close to Africa, it severed its history with that landmass a long, long time ago. So it remained connected to India. And 120 million years ago, it moved approximately to where it is today. It was only 88 million years ago that it became completely isolated and it broke away from India. And then India went north towards the Himalayas to form the Himalayas. So Madagascar's been an island for really only it's been about 90 million years. And this is a long period of time, and it's much older than a lot of the groups that live there are thought to have evolved.
The animals living on the island reflect this very distinctive geological history. Separated from Africa and Asia for millions of years, Madagascar has become a singular ecosystem, home to dozens of species that exist nowhere else on Earth.
Madagascar has some of the most unique and bizarre animals on the planet, and one of the most unique things about Madagascar is the fact that almost all the animals that are found in Madagascar are only found there, so no place else on the Earth. So one of the most famous groups that people associate with Madagascar is the lemurs. Lemurs are a very interesting group of primates. There's more than 100 species now recognized in Madagascar, and they're only found on the island, so they're completely endemic. Now, what's interesting about lemurs is that people have hypothesized how can there be primates in Madagascar when the group primates, which is found in other parts of the world, is actually younger than the separation. So people have really struggled with this question. If they weren't stranded when the island was separated, and if they didn't come across from Africa in some way, then how did they get here?
Madagascar's climate and soil type aren't conducive to the preservation of fossils. Karen and her team thus instigate a multitude of dig sites in the search for new clues. For the moment, given insufficient data, the origin of lemuroids on the island of Madagascar as yet remains unknown. Today, 3 hypotheses vie to explain the arrival of the first individuals. The first is that these animals appeared a very long time ago, well before the separation of India and Africa. The second hypothesis is that with changes in sea level, an ephemeral land bridge formed between Africa and Madagascar, allowing the primates to cross dry land. The final theory is the most astonishing. Lemurs arrived from Africa on makeshift rafts, carried by the sea and pushed by storms.
Well, we know that even the last 10 years, we've seen some storms bounce between Africa and Madagascar, even just a couple of days back and forth. And some have actually reconstructed that you could make a journey in less than 30 days if you were stranded on a raft. So when we talk about rafts, it could be something like this, or even something much bigger. In fact, we see in other parts of the world, people have witnessed giant masses of vegetation, even 1 or 2 kilometers long, that are carrying trees and animals and even a little pocket of fresh water. So in fact, there's actually many different types of ways that these animals could have come to Madagascar.
The raft theory seems implausible, and yet today it is considered the most probable hypothesis within the scientific community.
Some have said, that's crazy, the chances of success are very small. But then the other side has said, well, that's true, it's very small. But if you have, say, 100 million years or 200 million years, that even something that has a very small chance is sure to be successful. And so there's been a big debate about whether this is actually a reasonable explanation. But, you know, we've really had to try to reconcile the fact that most of the groups we see appear to have evolved after Madagascar was already an island. So right now, that's actually the most supported hypothesis to explain their presence. So the best evidence always would be direct evidence. And the best direct evidence is to find fossils of the right age.
Perhaps one day we will discover how these primates found nowhere else on the planet took up residence on this sister island of the African continent. But already their mere presence demonstrates how greatly plate tectonics can influence the destiny of a region and the species that live there. Separated from the other continents some 90 million years ago, Madagascar has become a distinctive ecosystem, very different from that of Africa. But even today, emerged lands continue their perpetual voyage across the Earth's surface. Africa as we know it represents just an ephemeral phase in the history of our planet. A giant scar cuts across the eastern face of the continent, the Great Rift. From Mozambique to Turkey, little by little it tears Africa in two. In a few million years, a new subcontinent will be born, Arabia. In parallel, Africa as a whole continues to move north. Its collision with Europe and Asia will thus take place tomorrow on a geological timescale. $300 million years ago, one vast supercontinent united all the planet's land masses. But Pangaea, as it is called, finally broke in two. Eurasia split off from what would become Africa and the other continents of the southern hemisphere. Between them, an ocean opened up, the Tethys Sea. The history of this marine expanse has left traces in the heart of one of the planet's most arid regions, the Arabian Peninsula. Here, the ground abounds with a precious resource, oil. The black gold has brought wealth to the Gulf states, and in particular to the Sultanate of Oman. The Wadi Nar Canyon in the north of the country is one of the places where indications of how it was formed are the most visible. Luwai Mashur is a geologist and oil prospector. In his expert view, Oman's situation today as an oil El Dorado is due to the presence of the age-old Tethys Sea.
We're in the heart of the Oman mountain range. The Tethys opened up in this region of the Arabian Plate. At that time, this whole area was underwater, hence the considerable sedimentation.
About 100 million years ago, Oman was located further south, a long way from the future Europe. Long before the desert and the mountains, the region was partially covered by the waters of the Tethys Sea. As the centuries passed, sediments were laid down over the seabed. The Tethys was warm and shallow, an ideal environment for bacteria to prosper, transforming matter into one particular substance, kerogen. 20 million years ago, however, the continents drew closer and the Tethys Sea closed up. The kerogen sank deeper into the ground. Under the effects of pressure, it transformed into hydrocarbons and seeped into the cracks in the rock. Luwai is prospecting throughout the region. He observes the rocks meticulously, looking for the slightest suggestion they could contain oil reserves.
A reservoir is like a sponge with little holes, and all these holes are filled with hydrocarbons or gas. We can see that this surface is ridden with cracks all along it, which were certainly caused by tectonic movements. If these cracks remain open, they improve the horizontal permeability of the rock and aid the circulation.
This area seems to be particularly rich in deep-set hydrocarbons. Studying the rock even closer, further indications confirm that the sea once came this far inland.
This is a fossil of coral, solitary, and so we can clearly see the structure, which is cellular and well preserved. So we have marine sedimentation here. Sedimentation in a sea that was quite shallow and quite warm.
By observing the rock around the cracks, Luwai confirms his initial analysis. The next step is to drill an exploration well to see if oil really exists deep underground. The Gulf countries of Iran and Iraq are today among the world's leading oil exporters. Symbolizing the emir's great wealth, the black gold is also the most precious of testimonies to the whole region's geological history. But the closure of the Tethys Ocean 20 million years ago left other traces too, that are rather more surprising. In Egypt, the majestic pyramids of Giza stand as a millennial legacy of ancient civilizations. But not far away in the Fayum Desert, the site of Wadi El Hitan contains other treasures several million years old. The roads here have given way to trails marked out in the sand. Improbably shaped stone giants rise up all around, sculpted by erosion over millions of years. Francis Duraton is a paleontologist and curator of the Toulouse Museum. For many years, he has traveled the world looking for fossils that can explain the evolution of species. Wadi El Hitan is of particular interest, as the desert sands here conceal some rather unusual bones.
Hello.
Hello.
Wow, you are digging?
Yes, make a small classification for a whale.
A whale? Can I help you digging?
Of course.
Yeah? Okay. And do you have a lot of whales here in the area?
Yeah, can you imagine we found like 1,000 whales in the area.
1,000?
Yes, 1,000.
Wow.
Nicknamed the Valley of Whales, the Wadi El Hitan site is a veritable open-air museum. The first bones were discovered here over a century ago by a British archaeologist. Since then, more than 1,000 whale skeletons have been found. As time goes by, the wind continues to blow away the sand, revealing even more relics.
It's surprising to find whale skeletons like this in the middle of the desert, but why are they here? Well, in fact, we're where the Tethys Sea used to be between about 37 and 40 million years ago. The sea was quite shallow here, and it was probably a lagoon area where these small whales, Dorodons, came to reproduce. The Dorodons were whales about 5 meters long, but they were prey to other much bigger whales called Basilosaurus, which could measure up to 18 meters. The small Dorodon skeletons we found, and particularly the young, have bite marks on them, meaning that they were the prey of the big Basilosaurus. So these animals came to reproduce in this region where the sea was about 30 meters deep. And when they died, obviously, they sank to the seabed and fossilized. Naturally, sediments subsequently accumulated over them. And when Africa rose up due to the plate tectonics, the sediment was removed and eroded, and so the whale remains were revealed and uncovered by the desert wind that they call here the Hamasine.
For the paleontologist, the Egyptian desert is an open book on the region's history. In the middle of the sand, whale skeletons lie alongside shark's teeth, fossilized mollusks, and even the bones of crocodiles and marine turtles. All these remains testify to the wealth and diversity of the Tethys Ocean's wildlife over 30 million years ago.
So the Tethys Sea was once a vast expanse linking the Atlantic Ocean to the Indian Ocean and the Pacific. Africa was completely isolated from Eurasia, and progressively, because of plate tectonics, the Arabic plate would open up and pivot because of the opening up of the Red Sea, and would close off this expansive sea to form what is today the Mediterranean Sea, a fragment of what the Tethys Sea once was.
The existence of this ocean today disappeared is the proof of the slow rise of the African continent and its collision with Europe. Today, only the Mediterranean Sea separates the two giants, but the voyage of the continents is not over. Slowly but surely, Africa continues to move northwards at a rate of 2 centimeters per year. The collision is underway, and it's in the Strait of Gibraltar that it's the most perceptible. At Al Hoceima in Morocco, the land quakes regularly from the effects of tectonic forces. On February 24, 2004, a quake measuring 6.3 on the Richter scale hit the city, causing over 600 victims. This formidable phenomenon has occurred at regular intervals. Philippe Vernon and Jean-François Ritz, geologists at the University of Montpellier, are currently working at Al Hoceima.
1.70 meters. Is the radio on? Okay, we're off. North on the surface. You head west and go as far as T1. Then you take T3 and come back.
The scientists want to make precise models of the tectonic movements the African plate undergoes in contact with Europe. Armed with their GPS, they explore the area, taking extremely precise topographical readings.
The idea is to mark out an itinerary that will enable us to accurately measure the topography of the different areas we see here, and the whole profile, which forms a basic rectangle and allows us to see the difference in height of the various areas. Notably here, for example, at the point T3, which is an old riverbed that has risen up, there's the river today. We can get a very precise measurement of the height difference between the old and new beds. So we've crossed east to west, and we have the Cape Point here. You went to T3, and here's the north-south profile, where we'll take the samples of the pebbles. Here we have an active riverbed, but what we can see in the landscape is that the river used to flow here. That's the initial level. In fact, the river sank into the ground. It sank because the Earth's crust rose at this point, and where they are, up there, there are also pebbles, which shows that there was an uplift here of about 40 meters. What we want to quantify is the rate of that uplift. To do that, we have to do two things. We have to measure the exact height difference between the two riverbeds, the current one and the old one, and then we have to date the pebble deposits up there. So if we have those two pieces of information, we divide the height by the age, and we get the rate of uplift.
Throughout the region, the ground sinks and rises and fractures. The collision between Africa and Europe causes the rock to fold and numerous fault ruptures appear. An analysis of the GPS data will soon enable the scientists to understand the scale of the movements. A few days later, Philippe Vernon and Jean-François Ritz are back at work. This time, they've traded their GPS equipment for ropes and harnesses. They're focusing on a rocky cliff a few dozen meters high. The aim is to reconstitute the chronology of the earthquakes that led to the appearance of this fault.
Okay, Phil, pull it up.
It's okay, I've got it.
In order to date previous quakes, the scientists use a rather particular technique, dating by cosmic rays.
Okay, it's taut.
The Earth is constantly being struck by particles from space. When they hit the ground, they're absorbed by the surface rocks, whose composition is slightly altered. With each seismic event, the ground fractures and new rocks are exposed. By analyzing the surfaces, the scientists can determine how long each strata was exposed to the cosmic rays, and therefore date the successive quakes. The height of each uplift also provides precise indications of the magnitude of the event. On the ground, the geologists take rock samples from along the top of the cliff.
If we take samples from all along this surface, we should be able to see that it's older up above. So that means we're seeing a quake, and then we can see a different period below, with another quake, more recent, and so on, moving to the bottom. So we can see the history of the different seismic events which led to the formation of this fault plane. And so that tells us something of the region's seismic destiny. Every so many years, in fact, there was an earthquake which led to this, and depending on the movement, we can get an idea of the magnitude of the events.
Characterizing the various quakes that shook the region over thousands of years will enable the scientists to gain a better understanding of the movements that affect the African continent.
6.5, 7 here. We can take 6.5 probably.
This study will ultimately contribute to making more precise predictions of quakes in the Al Hoceima region, for the land continues to tremble here inexorably. The movement of Africa towards Europe is a fundamental action that nothing can stop. Little by little, the Strait of Gibraltar will close up. And in about 50 million years, the Mediterranean Sea will have almost disappeared. But as Europe and Africa face off at Gibraltar, another plate steps into the dance in the east: Arabia. Arabia is gradually separating from the Sinai region and moving northwards. The rate of this movement is greater than in East Africa. The result is that the two plates slide against one another, and in the middle, a gigantic fault has appeared. Known as the Dead Sea Transform or Dead Sea Rift, it splits the Near East from the Red Sea to Turkey. Between Jordan, Israel, and Palestine, this sliding movement of the plates has led to the collapse of a whole region, in the middle of which is the Dead Sea. High up on a rocky spur, the fortress of Masada in Israel benefits from a unique viewpoint over the whole region. This is where Jan Klinger is heading. A geologist from the Global Physics Institute in Paris, he has been traveling the region for many years. His objective is to understand the movements that have affected the Dead Sea Rift over previous millennia. Above the sheer cliff, the majestic fortress dominates a lunar landscape framing the Dead Sea and the Judean desert.
Here we're on the Masada Plateau. We're above the Dead Sea, which is 400 meters below sea level, so 400 meters beneath our feet, more or less. The plateau here is part of the Sinai Plate. We're standing over this vast depression filled by the Dead Sea, which is associated with the activity of the Dead Sea Transform. The fault is about 1,200 kilometers long, and it enables the Arabian Plate to move northward compared to the Sinai Plate here to the west.
The sliding movement of the tectonic plates has for a long time produced powerful seismic events in the region. But their magnitude and above all their frequency are still little known. To improve predictions of future earthquakes, Jan is attempting to compose a complete picture of previous events. And so he explores the Dead Sea Basin accompanied by geologist Shmulik Marko from the University of Tel Aviv.
So the fault is running here. Each time they move, they create an earthquake. Okay, right?
The rocks here store records of the alternating dry and rainy seasons, and above all, of each time the Earth shook. By studying the overlying strata, the scientists can literally go back in time and retrace the tectonic history of the Dead Sea Rift.
We see two different layers here, one dark and one white. The white ones were deposited in the summers, and the dark ones are the winter deposits, flash floods that came into the lake, deposited fine material, and actually each pair is 1 year.
So we can count years.
Yes, exactly.
Okay, right. And we have a huge deformation here. Huh? What is it, this thing here?
Yes, here we have, we see folded layers. We see that we can follow these and up and down, and in this quiet environment, the only thing that can set a layer to slump like this is an earthquake.
So all this layer, for example, it just get folded like this when it was flat before, right?
Yes.
And this is a signature of an earthquake?
Yes.
And you have a series of things like this here that gives you chronology of past earthquakes on the Dead Sea Fault here.
Exactly. We don't have seismographs at this time, and we have about 50,000 years of record.
Okay.
And we have about 30 strong earthquakes that happened in this period.
So you make a catalog here?
Yes, it's an archive of earthquakes.
Hey, what about these tiny things? It looks like the layers. Are there a fault here maybe or something?
Yeah, it's a fault.
Nature conserves traces of the seismic events that shape it, but sometimes our own history has a story to tell too. Working in a region with such a rich 2,000-year-old history is a godsend for geologists. In the north of Israel, the ruins of the Vadum Jacob Templar Castle also tell the tale of the Dead Sea Rift. In 1178, Christian armies built this fortress to prevent the Muslims from reconquering Jerusalem. The Christians would finally lose that war, and the Vadum Jacob was partially razed by the enemy. But the site was doomed anyway. The Crusaders, in fact, had built on the fault line itself along the course of the River Jordan.
Here in this castle, for example, we can see that this wall has shifted. This part of the wall has moved towards me, whereas that part has moved to the north. This is the limit between the Arabian plate on this side and the Sinai plate on this side. So we can reconstruct the history of earthquakes here through the archaeological remains, and from the geological records we can find in the area too. So far away from the fault line, the movement is continual and imperceptible to man of around 5 millimeters per year. But here at the fault, we can see that there's no movement. Forces build up, and at some point, those forces exceed the resistance of the Earth's crust, and there's a tremor. And so, all along this fault, there are regular seismic events in response to the accumulating forces here, resisting the 5 millimeters per year movements, which are continual.
Thanks to historical writings and archaeological digs, the date of the first earthquake to hit the castle has been determined. It took place on May 20th, 1202, and moved the walls by 1.60 meters in just a few seconds.
So here we're on the other side of the castle, and of course the fault crosses these walls too. As we go along the wall, there's a gap of over 2 meters. So naturally, this fault is an integral part of the Eastern Mediterranean regional geodynamics, and when the Arabian plate moves northward, it needs space. It creates space by building mountains along its front and by pushing the Turkish plate to the west to continue on its way forward. These faults are the translation of plate tectonics, and plate tectonics are in action on our planet. They will never stop. It creates topography, it causes movements which are locally violent in the form of earthquakes, and it's something that totally goes beyond human timescales, and which will continue.
Arabia today continues to move inexorably to the north, millimeter by millimeter. In the future, no doubt other earthquakes will strike the region and further deepen the Dead Sea Rift. A little further south, the separation of Africa and Arabia occurs rather differently. Over the past 20 million years, the two plates have been progressively moving apart at a rate of 15 millimeters per year. And in the middle, a new ocean is being born. For the moment, it is merely a sound, a maximum of 300 kilometers wide. It is called the Red Sea, prolonged in the east by the Gulf of Aden. Off the Sultanate of Oman, the small island of Al-Alania is an ideal study site for understanding the impact of the opening of the sea. The ground is often shaken here as the plates move apart. Félicie Koristelev and Jordan Corbeau work at the Jussieu University in Paris. Their research subject is the movement affecting the coast along the Gulf of Aden due to tectonic forces. They're going to Al-Alania to collect a seismograph installed here several months ago. The island is an exceptional site for seismic analysis. It has very few inhabitants, no significant buildings, and only a single, little-used road. There are no vibrations caused by man which could pollute the data recorded. We've set up about 20 stations in the south of Oman, in the Dhofar region. This is the last station we're collecting. All the others have already been collected. Once we've got it, we'll send it to France to analyze the data. We obtain recordings of ground movements, of movements due to earthquakes in particular, and so we can therefore study the internal structure of the ground beneath the region. The network of seismographs makes continual recordings of even the slightest earthquakes. Each quake reflects an event of greater amplitude that occurs a few kilometers offshore in the depths of the Gulf of Aden. At the point where Africa and Arabia are moving apart, a vast depression has been created, and the sea has moved in between the two continents. Over the centuries, the Earth's crust continues to be stretched. Magma spurts up from deep within the mantle and fills the empty space created by the separation of the plates. This then forms what is known as a mid-ocean ridge.
Seismological stations have been set up along the coast of Oman to map Oman's continental margin, and subsequently the opening up of the Gulf of Aden. The continental margin is the transition between the continental crust, characteristic of continents, and the oceanic crust, which is typical of oceans. The Gulf of Aden margin is interesting because it's currently being formed, so it's in the opening phase, moving from a continental crust to becoming an oceanic crust. So we're here facing the seafloor spreading between the Arabian plate and the African plate.
The two scientists have gathered a massive amount of information during their mission. Analyzing it all will take time. But one day they hope this study will enable a detailed modeling of the opening up of a new ocean. The Sultanate of Oman is also the scene of another scientific team's field study. Their investigation is taking place not far from the town of Mirbat on the shores of the Arabian Sea. Sonia Roos and Melina Makouin are geologists from the Research Institute for Development in Toulouse. Their mission is to determine the date of the opening up of the Gulf of Aden. To do this, they're studying rather particular rocks known as dikes.
I think we're on this one, right?
We'll have to go and see it.
The dikes were formed 700 million years ago when the Arabian and African plates were joined. Within the seams of this magmatic rock are tiny crystals containing iron. It is this metal that is of interest to the scientists. Its presence confers the dikes with a specific magnetism. Analyzing this can enable even the slightest movements on the Earth's surface to be retraced.
These very old dikes can be found on the other side, on the African plate. We have exactly the same dikes, the same age. When we put them together, we can define the rotations of the various geological formations and see to what extent we can reassociate them.
To find out when the Arabian and African dikes began to separate, the scientists take a series of samples along the coast.
Concerning the past 30 million years, for the Gulf of Aden, for example, we're looking at sea for magnetic anomalies, and we can also look on land for the information we're lacking, and which will perhaps help to determine the period when the Gulf opened up and the two plates separated.
It will take several months more work to know exactly when Arabia began to leave Africa and understand the movements the two plates underwent. Today, the two continents are almost completely independent. A little further south, a single land bridge still links the two plates. This region is known as the Afar Triangle. In a few million years, this corner of Africa, overlapping Ethiopia, Djibouti, and Eritrea, will in turn break off and move away with the Arabian Plate. The land here is fractured and fragmented. The tearing and straining of land masses leads to the ground collapsing and violent volcanic eruptions. The area is 100 meters below sea level. And exceptionally, the formation of a mid-ocean ridge can be studied on land here. In the easternmost part of Ethiopia, the Erta Ale volcano is one of the region's mythical emblems. All around is a tortuous landscape where sulfur deposits and lava flows stretch as far as the eye can see. This desert, one of the most arid in the world, is home to the Afar people, semi-nomadic herdsmen and renowned warriors. The volcano Erta Ale rises up to an altitude of 613 meters. It is one of only a few in the world to have a permanent lava lake at its summit. Before his death, the eminent volcanologist Jean-Louis Cheminée was fascinated by this extraordinary smoke-shrouded mountain, which he visited regularly with his team. With lava samples, gas analyses, and rock composition studies, the specialists have examined the volcano in every detail. They have gradually improved their understanding of how a new ocean is formed. But Erta Ale will continue to fascinate scientists for a long time to come. The spectacle it proposes here is unique in the world, a symbol of the link uniting geologists and volcanoes. In Djibouti, the Goubet al-Karab marks the southeast point of the Afar Triangle. This deep-water bay, surrounded by steep cliffs, is linked to the sea by a channel with very strong currents. At one end is the Ardukoba volcano, which last erupted in 1978. That eruption spat out more than 12 million cubic meters of lava, transforming the landscape into a lunar panorama. On the other side of the volcano is Lake Assal. Once filled with fresh water, it is today increasingly salty. As the land spreads and opens up, the sea gradually moves in. For several years now, Bernard Legal from the University of Brest has been monitoring the separation of the tectonic plates. He's seeking to understand exactly how the Earth's crust is transformed into an ocean floor.
This is an exceptional geological site. We're looking at Lake Assal, which is located 150 meters below the level of the Goubet Gulf. From here, we can clearly see the overall morphology, where the lopsided relief behind is composed of the oldest lava in this sector, about 3 million years old, whereas the lava covering the base of the depression is much more recent, only a few thousand years old. Here we're on the surface of one of the very recent lava fields. If we consider the geochemical composition of the lava fields in the Assal Goubet area, we can see that it's very comparable to the oceanic basalt, which forms the bed of the current oceans.
By studying the chemistry of the recent rocks, the scientists have taken a first step in demonstrating that an oceanic crust is in the process of replacing the desert landscape here. It's an exceptional geological spectacle, which normally occurs out of sight, deep down in the depths of the ocean.
Geophysical studies have shown that beneath the Assal Depression, the crust was very, very thin. The crust is about 4 to 5 kilometers thick, which means that deep down the crust must be injected with matter from a great depth, and that it's probably already reached the point of rupture. And so this means that here in front of us, we're witnessing a process of magmatic accretion with the creation of a new crust of an oceanic type.
Magmatic accretion is the term to describe the rising of magma from the mantle and the gradual formation of an oceanic ridge.
If we apply the current rate of separation, which is about 2 centimeters per year, to the future, then it's probable that this zone of accretion at Lake Assal will be about 20 kilometers wide in 1 million years' time and 200 kilometers wide in 10 million years. As the region undergoes accretion, it will also become deeper, and it will progressively be flooded by seawater, which is now at the level of the Goubet Gulf. If we compare mid-ocean ridges with a sort of continental fracture which spreads, then this would be like the top of a zipper which is opening up.
It's hard to imagine that here, in a few tens of millions of years, we'll be underwater, several hundred meters below the surface. But the forces which affect the whole region don't stop there. To the south of the Afar Triangle, another grand-scale phenomena is occurring. A huge scar splits all of the east of Africa, the Great Rift Valley, a fault line extending over 6,000 kilometers from Ethiopia as far as Mozambique. Beneath the surface, the continental plates are pulling apart approximately 1 centimeter per year. In about 100 million years, an ocean will split Africa in two. But for the moment, the rift is composed of a vast, deep valley several kilometers wide. In Mozambique, the Gorongosa National Park is located at the southernmost point of the rift. Martin Pickford is a paleontologist at the Natural History Museum in Paris. For an explorer seeking clues to the history of the Earth, the valley is of great interest.
Okay. Oh, that's magnificent, no? We have the rift here and Lake Orima in the background there.
The appearance of the rift millions of years ago led to the whole valley collapsing. The sea swept into the fault on several occasions, depositing countless layers of sediment. Within the valley, thousands of bones were fossilized in ideal conditions and have survived throughout the ages untouched by the ravages of time. Today, erosion has brought a myriad of fossils to the surface.
Looks like a fragment of the pelvis. There's the acetabulum here. Bit of sediment stuck on it here. But it's in terrible condition. Difficult to identify. But at least it shows there's fossils, bones have been fossilized in this area.
Martin Pickford is particularly interested in the origins of mankind. In the year 2000, it was in the heart of this rift valley that he made an exceptional discovery: the remains of Orrorin, a hominid some 6 million years old. Martin believes the formation of the rift could have contributed to the appearance of our distant ancestors. Tectonic forces would have led to a profound transformation of the landscape. Whereas tropical forest covered western Africa, savanna now dominated the eastern part of the rift. The first men could have well settled in this new, more hospitable environment. They would have evolved very differently from their cousins, the great apes, more adapted to a forest milieu.
Actually, the Eastern Rift is the resulting savanna fauna that we see today, giraffes, hyenas, lions. It's actually a result of two movements, one from the south, installing some animals and plants, and one from the north, installing other animals and plants. And that's really the importance of the rift, and the rifting, the tectonics, changes the climate, changes the vegetation, and of course the animals move as the situation changes, as the conditions change. Homo actually evolved not in the rift itself in East Africa, but somewhere else and then came in. Because when you find it, the stone tools and so on, almost in every locality. And before that, there's nothing. They come in and then they're Homo. Here we have a gallery going into the side of the cliff, and we can see it goes into a cave at the end. It opens up into a ravine at the side. So were early humans living here, or maybe one of them might have fallen into the cavity and got fossilized? We need to go and excavate to be sure. But when you think there's hundreds of kilometers of these gorges in this region, the chances are there's at least several of these caves probably have early hominid remains in. And I just have a feeling that it will yield interesting information. Okay, it's just big enough for a human to come inside. And, oh, there we are. Oh, here there's a recent infilling of sand, but some of these will have old deposits which have turned to stone, and in those we can find bones and snails, bits of wood, and that sort of thing.
The theory that the rift played a major role in the appearance of humans is the subject of widespread debate. But for Martin Pickford, our planet would no doubt be very different if the Earth had not shifted and opened up in East Africa.
So strange to think that if it hadn't been for plate tectonics and all this global activity, climate change and so on, humans wouldn't be here today. In fact, I wouldn't even be here looking at the Rift Valley. In a manner of speaking, it should still be the planet of the apes. Strange, but probably true.
In Africa, like everywhere else, evolution is intimately linked to the history of the land. Man today has conquered the whole planet and extended his dominion over every natural milieu. But will he still be here tomorrow to witness the transformation of the African continent? In a few million years, Africa and Europe will form a single continent. As for the Red Sea and the Gulf of Aden, they will become vast oceans. And for the first time in its history, the heart of Africa will be split in two. The eastern part will begin a long journey across the Indian Ocean, drifting according to the movement of the tectonic plates and possible collisions. The all-powerful tectonic forces have not yet drawn up the definitive contours of the African continent. Straddling mountains and oceans, Central America boasts a wide range of exceptional landscapes. To the east, speckled with countless archipelagos, the Caribbean Sea faces the mighty Atlantic Ocean. To the west, a thin ribbon of land stretches from Mexico to northern Colombia and the shores of the Pacific. The history of this region is unique in planet Earth's epic journey. Whereas most of the continents are several billion years old, Central America is much younger, emerging from the depths of the sea only 150 million years ago. Understanding every detail and every step in the formation of this territory is the main objective for Thierry Calmes, a scientist from the Geology Institute at the National Autonomous University of Mexico. His field of study is in the north of Mexico, not far from the town of Hermosillo, the capital of the state of Sonora. We're in the heart of the western Sierra Madre, a range of mountains stretching over 100 kilometers across the country. These peaks are the vestiges of the very first moments of the creation of western Mexico. About 200 million years ago, the future North and South Americas began to slowly drift westwards. They hit an oceanic plate, the ancestor of the Pacific Ocean. Named the Farallon Plate, it started to disappear between the Earth's mantle.
This famous Farallon Plate gradually sank between 200 million and 20 million years ago beneath the North and South American plates. This subduction caused plutonic magma phenomena, which means the intrusion of deep-set magmatic rock and volcanism, which is magmatic rock reaching the surface. That was the case here in the western Sierra Madre, where we have perfectly typical relief related to that subduction phenomenon.
Thierry Calmes is looking for the last vestiges of the Farallon Plate, which has today almost totally disappeared. He heads for the La Caridad mine, one of the world's biggest copper mines. The mountain here has been sliced apart over thousands of square meters. For this scientist, the exposed rock becomes an open book on geological history.
We're here for one very simple reason. Plates disappear, and most of the Farallon Plate has disappeared due to subduction. Fortunately, we have witnesses, like today's volcanoes are witnesses to current subduction processes. We have witnesses to the historic subduction, which occurred between 200 million and 20 million years ago. And among these witnesses, we have these copper mines, which are connected to the magmatism associated with the subduction of the Farallon Plate.
The copper in the La Caridad mine, in fact, comes directly from the ocean floor that made up the Farallon Plate. When the plate sank beneath the North American plate, the precious mineral was swept away by water and magma, then rose through cracks within the continental crust. These copper deposits were therefore the direct result of that age-old collision. By taking extensive samples, Thierry Calmes and his team hope to get a better understanding of the slightest movements that affected the region millions of years ago. Through its very disappearance, the Farallon Plate triggered the construction of Central America. It also gave way to another oceanic plate situated just behind it, the Pacific Plate. And 150 million years ago, a major event occurred in the middle of this ocean. the birth of the Caribbean plate. Traces of this phenomenon can be seen today in the heart of the Antilles archipelago on the island of La Désirade. Here the waves of the Caribbean Sea roll in along a jagged, rocky coastline. The beaches are covered with volcanic rocks and gigantic domes of basalt. This tortuous landscape is an ideal study subject for French geologists Luc Legendre and François Michel. They're looking for clues concerning the formation of the Caribbean plate.
Here are the volcanic tuff rocks.
It's magnificent.
Pillow lava, quite exceptional.
Pillow lava is an English term. In French, we would say coussins de lave, or cushions. And these pillow lava are formed at the bottom of the ocean, 2, 3, or 4,000 meters down, under the pressure of cold water. We can see the base and imagine that the lava that emerges is hot, at around 1,000 or 1,200 degrees, and it forms this bubble which cools very rapidly. We can clearly see here a sort of cortex around it, a kind of envelope, which cooled more quickly. If we look at the pillow lava below, we can see below the cortex an area of bubbles, and then the heart here, which is basalt, and so on, it accumulated like that. It's magnificent.
For the experts, these lava pillows provide unique testimony to the formation of the Caribbean plate at the bottom of the ocean. They are the result of intense volcanic activity at what are called hotspots, regions of the Earth's surface where the temperature below the surface is particularly high all the time. Vast quantities of magma rise to the surface from the depths, accumulate beneath the surface, then spread out over the seabed. The oceanic crust thickens in places and finally gives rise to a new tectonic plate.
Here we are with our bathyscaphe, 150 million years ago, looking at the seabed with the lava arriving and the pillow lava forming.
It would be good if you could tell us the age of these pillow lava.
What we've been able to date are the radiolarites. The radiolarites we have here beneath our feet contain microfossils that provide us with an age. These are from the end of the Jurassic. That would be 145 to 150 million years ago. These microfossils are characteristic of that period. We're in the presence of the oldest rocks in the region.
It's also important to say that at the end of the Jurassic, 145 to 150 million years ago, the Atlantic Ocean was just beginning to open up. And here, in a way, we're in the Pacific.
Oh, yes, and that's a puzzle. In fact, geologists have been wondering for decades about these rocks and their origins. Thanks to all their studies, we now know that here on La Désirade, we have testimony to the beginning of the formation of the Caribbean, tectonically speaking.
For a long time, the date, and above all, the location of the Caribbean plate's formation, were a mystery for the specialists. But these rocky formations on the island of La Désirade provide the proof of its emergence from the heart of the Pacific Ocean, thousands of kilometers to the west of the Americas. Subsequently, the American plates continued to drift slowly to the west. The result was that the Caribbean plate gradually slid between the two giants.
We have here extremely rare testimony to the formation of the Caribbean plate 150 million years ago in the Pacific. This mass of rock that we're looking at was formed in the Pacific And it was only gradually that the two Americas moved to the west and the Caribbean plate managed to insert itself, like with forceps, we could say, between the two massive blocks to the north and south.
Approximately 100 million years ago, the young Caribbean plate reached its current position in the tropics, on the edges of the Atlantic and Pacific plates. To learn more about the region's subsequent history, François Michel continues to explore the coast of La Désirade, seeking out more clues.
Here we have another outcrop of rock, and we find the same basalt we saw at the last outcrop. These rocks are very old, about 150 million years old. And we find them in the form of pebbles, these dark pebbles, which are very, very old. And they're a complete contrast to the lighter pebbles, which are much more recent, and a part of a whole other story, almost contemporary, from the last few thousands or hundreds of thousands of years that we can find on the terraces above us.
The southern shore of the island is lined with a terrace of varying width, rising about 20 meters above sea level. As he observes the rock strata above Mao Bay, the geologist can almost completely reconstitute La Désirade's geological past.
Here at Maho Bay, we see a new outcrop where the base is made up of the same basalt we saw before, the pillow lava about 150 million years old. And above that, there's a marine terrace which tells us a whole other story. This is 150 million years old, and this is 120,000 years old, as the sea gradually rises. It laid down, as we can clearly see here, an initial layer of rock, mainly composed of pebbles and gravel, and an accumulation of shells. We call that a conglomerate. And when the level of the sea rose, we can see that something else settled with a very different aspect, and that's quite simply a coral reef, a barrier reef. So here we have both the oldest rocks in the Caribbean and no doubt the youngest too in terms of geological history. Between the two, a fantastic amount of time passed, a period that saw the birth of the Caribbean plate.
Over millions of years, therefore, the Caribbean plate underwent numerous dramatic changes. The sea level rose, then fell, until the landscape we know today appeared. But on its eastern side, the Caribbean experienced a very different and much more violent phenomenon, its encounter with the Atlantic Ocean. The two oceanic plates collided, and the denser Atlantic plate slid below the Caribbean plate. At the point of contact, the rock fractured and split. Magma rose up from deep down, and an arc of volcanic islands was formed above the waves. In the heart of the Lesser Antilles, the La Soufrière volcano is the best-known testimony to this collision, which is still going on today. It's located on Guadeloupe, about 10 kilometers from the town of Basse-Terre. On the slopes of the volcano stands Guadeloupe's Volcanological Observatory. Research workers here have front row seats to observe the activity of the barely dormant monster. A team of volcanologists is today setting out on a field trip. Their destination is not easy to get to, so Dominique Gibert from the Global Physics Institute in Paris has to be lowered down by helicopter along with his team. They've brought with them a cutting-edge apparatus, a geological scanner which enables them to see inside the volcano.
So here we're unpacking a cosmic ray telescope, It's a prototype composed of particle detectors that we can see here, the yellow frames, which measure the quantity of cosmic particles that go through the volcano. By doing this kind of reading, we can determine the density of the dome. As the denser the rock, the more it stops the particles. So we can make X-rays of the volcano with this telescope.
For hours, the whole surface of the volcano is subjected to the scanner's scrutiny. A spectrum of colors emerges, representing the density of each type of rock. The red zones correspond to the densest and most solid areas. The blue zones to the most fragile.
The interest of these experiments and of these radiographs is that they provide us with information about the volcano's structure. When it was formed, it was composed of quite new, robust lava, and it had a fairly stable form. Since its formation, the volcano has been infiltrated by extremely acidic fluids, which come from the hydrothermal system and which eat away at the interior. So the volcano is now likely to collapse because it's lost a good deal of its mechanical cohesion. This could involve the collapse of a single sector or the whole thing. And the radiographs that we've done tell us about the size and the number of zones affected which could collapse in the event of an earthquake.
The weather is unpredictable in the tropics, and the work on the ground is long and fastidious. The scientists have to move the telescope regularly in order to examine the volcano from different angles.
We now have a good deal of data and can combine it all to try to do what we do in medicine, which is to create a 3D image, like with a scanner, combining the various angles that we've examined with the telescope. It's been here for about 3 months. It was previously in the south, then to the east of the dome. So we have 3 different viewpoints, which should allow us to make a 3D reconstruction of the internal structure.
The first results obtained using the revolutionary telescope reveal the fragility of La Soufrière. Eaten away from inside, the base of the volcano could collapse at the slightest tremor. Such a catastrophe would have potentially appalling consequences for the 12,000 inhabitants of Basse-Terre. La Soufrière and many other volcanoes of the Antilles archipelago embody the violent encounter between the Caribbean plate and the Atlantic Ocean. 4,000 kilometers away, an identical phenomenon is underway. On the western side, the Caribbean plate and the southernmost point of the North American continent are being shaken by another ocean, the Pacific. The Pacific plate is gradually being drawn downwards. And once again, the contact between the plates leads to the emergence of new volcanoes. The latest rose from the land less than a century ago, barely yesterday on a geological timescale. It's February 20th, 1943. Dioniso Pulido, a Mexican farmer, is inspecting his fields after a long day's work. He discovers a thick layer of ash that is still hot. All around, fumaroles emerge from the bowels of the earth. After 4 days of constant rumbling, a 60-meter-high volcano appears. It grows very quickly, throwing out astronomical quantities of lava and ash which destroy the neighboring villages. Named Paricutin, it is one of the rare volcanoes on the planet to have emerged as man looked on. A further addition to the long volcanic belt that stretches all along the west coast of Mexico. Not far away, the Nevado de Toluca appeared several million years ago. At 4,690 meters high, it's the 4th highest peak in the country. The volcano is today extinct, and its summit cradles 2 vast craters filled with crystal clear lakes. This grandiose setting is one of the hunting grounds of geologist José Luis Arce from Mexico's National Autonomous University. His aim is to gain a fuller understanding of the geological history of a region home to the greatest concentration of volcanoes in the Americas.
We're in the central part of Mexico, where volcanism is due to the subduction of part of the Pacific plate under the North American plate. This subduction produces volcanism. At Nevado de Toluca, we can clearly see this big crater, which is 2 kilometers wide and 1.5 kilometers long. This volcano is part of the Pacific's Ring of Fire.
The Ring of Fire José Luis Arce refers to is the gigantic horseshoe-shaped volcanic arc around the Pacific Ocean, from Indonesia to Canada and from North America to the south of Chile.
The Pacific Ring of Fire is an area along the edges of the plates. It coincides with a great number of active volcanoes all around the Pacific. This generally corresponds to subduction zones. There are active volcanoes and significant seismic activity, and this is due to the interaction between the plates.
But along the west coast of Mexico, the subduction of the oceanic plate does not occur in a perfectly linear manner. The degree of inclination varies, and so the volcanoes appear inland at differing distances from the sea.
For Mexico, it's rather particular, as the subduction is not parallel to the Mexican volcanic belt. There are various angles of subduction. In the western part of Mexico, the subduction is quite inclined, whereas in central Mexico, it's flatter. And this is why the volcanoes are further away from the subduction zone.
In the Mexico City Valley, another volcano, Xitle, left a fatal and indelible mark on the country's history. It erupted almost 1,300 years ago, totally destroying the town of Cuicuilco, at the time one of South America's most prosperous cities. José Luis Arce meets Maria Sandoval González, the archaeologist in charge of the site. Together, they explore the archaeological remains, looking for traces of ancient lava flows.
We have lava here, volcanic rock. The bubbles indicate that they contained gases, mostly CO2 and water vapor. These gases separate from the lava as it advances, and the bubbles deform as they're crushed.
This lava covered the city of Cuicuilco. It was buried in around 750 AD by the volcano Xitle, which is to the south of Mexico City.
We can see various structures here. These are lava flows. These structures are like wrinkles which form when the lava moves forward. It advances and leaves these lines.
Because it gets colder?
Yes, it advances and gets colder at the same time and leaves these marks, which give us an idea of the direction of the flow.
Like an American Pompeii, the city of Cuicuilco is today a major archaeological site. Valuable testimony recalling that geological history can be inexorably intertwined with that of mankind. In Central America, however, volcanic eruptions are not the only threat to the inhabitants. Wherever plates meet, tectonic movements regularly cause tremendous underwater earthquakes. These can then lead to the formation of colossal waves and even tsunamis. According to the experts, the Northern Caribbean is particularly at risk. Over the past 500 years, more than 50 tsunamis have already been recorded. Along the eastern rim, the Lesser Antilles region is being closely monitored. The Advanced Lookout Station is in Guadeloupe at the Volcanology and Seismology Observatory. Its director, Daniel Amarez, is today accompanying Sébastien de Russi on a trip to gather the data recorded by a whole network of sensors.
Well, the building's in good condition. It hasn't moved recently.
One of the roles of the Volcanology and Seismology Observatory in Guadeloupe is to take part in the tsunami watch. The main cause is seismic activity, which we can observe at the interface between the Caribbean and the North American plates in the subduction zone, about 100 kilometers from here. Did you check the supply recently?
Yes, it's picking up the satellites. Everything looks good.
To evaluate the risks of tsunamis in real time, tide gauges are deployed throughout the region. These instruments constantly record the slightest change in the sea level.
If a tsunami is triggered in the region, then everyone around the basin will be affected. The instruments that we use here, like this tide gauge, are able to detect a wave that's already passed. So in a way, it would already be too late. But it will be useful for the people in surrounding countries, further away. In return, our colleagues around the Caribbean basin have other instruments which are useful for us. So we really have to regard this system as being of global value. We can't simply have a tsunami alert system all alone in isolation. It wouldn't work, because tsunamis cross whole oceans, and it takes time for them to cross oceans and seas. And it's that time that enables us to warn people.
An earthquake in the northern part of the Caribbean plate could generate waves of more than 12 meters and endanger the lives of some 35 million people. The tectonic forces in action in the Northern Caribbean have always shaped and modeled the region. Millions of years ago, volcanic islands emerged from the waves, and tomorrow, they will perhaps be swallowed up by a tsunami. But the collision between the Caribbean plate and the Atlantic Ocean also causes slow vertical movements in the seabed. This phenomenon lies behind the emergence or the submersion of certain fragments of the Earth's crust. In Guadeloupe, the island of Grande Terre is the direct result of these constant movements. The rock strata here bears witness to a turbulent past. The island has undergone a succession of both marine and terrestrial events over several million years. Jean-Frédéric Lebrun and Jean-Laurent Letissé are geologists at the Antilles University. For several years now, they have been trying to reconstruct Grande Terre's complex geological history. Today, they're in the town of Sainte-Anne exploring a quarry.
That's what we call white limestone. It's dazzling.
In the heart of the limestone massif, the scientists look for very particular clues. Fossilized coral, which show that the area was once covered by the sea.
Look, there's one there too, an agaricea. In fact, we can find all the corals we usually see in quite deep reefs. In calm zones, which enable the limestone mud to settle and to construct this whole formation. So this quarry is quite exceptional, because there are two reefs, one on top of the other. At the bottom, there's the agaric limestone, which is about 40 meters thick, all the same. And then there's an eroded surface, which goes down and which undulates, because there are channels which have been dug out and it continues down there. The eroded surface has recorded a lowering in the sea level. The sea went down, and erosion carved out the cliff.
The sea level therefore went down. Subsequently, the level varied further, and the sea rose slowly, bringing sand with it. This sand was deposited on the coral reef until it was completely covered.
So we can see that it's getting higher. The sea level rises, and the beaches advance and move on, and they reach as far as up there. On the top, we can see a second reef, an acropora reef, which looks quite granular from here. So that's the second reef that's settled on the top, and that represents the stabilization of the higher sea level.
After the second flooding, Grande Terre experienced a final dramatic change due to the effects of subduction. Around 400,000 years ago, it surfaced once more, becoming the island we know today. As time goes by, Jean-Frédéric Lebrun and his colleagues learn ever more about the history of the Antilles. But the tectonic phenomenon at play here are complex. In their laboratory, a map of the region reveals a disparate tangle of faults on the edge of the plates.
This is a bathymetrical and topographical map. It shows the region's relief. And so Guadeloupe and La Soufrière are right here. And this is the arc of volcanic islands, with Dominica here, the Saints Islands, and Basse-Terre. What's interesting on this map is that we can clearly see all the structures, all the faults. The faults are connected to an opening towards the north. The front part of the arc is drawn to the north because of the subduction, which occurs obliquely in this region, and so it's cut all these faults. We can see here, for example, the Mont Piton fault, which we can clearly see on Marie Galante. It's like a step, and it goes from here to there, so it's almost 60 kilometers long. This part has gone down, and this part has risen.
A few kilometers south of Grande Terre, the island of Marie Galante is cut in two by a gigantic fault, which has widened gradually over the centuries. Several dozen faults split the land all around Guadeloupe. A little further north, the Greater Antilles archipelago is subjected to the same tectonic stress. And here, the confrontation of the Caribbean and North American plates has even more spectacular consequences. Instead of going one under the other, according to the subduction phenomenon, the two plates slip against one another, and in the middle, another gigantic fault has appeared. Haiti and its capital, Port-au-Prince, are smack in the middle of this displacement zone. On January 12, 2010, an earthquake of a magnitude of 7 devastated the country, causing more than 230,000 victims. Even today, Haiti is still attempting to heal its wounds. Port-au-Prince is slowly getting back to normal, but the scars of the catastrophe are still only too visible. This deadly earthquake sounded the alarm among the international community. there is an urgent need to predict future quakes as early as possible. An intensive surveillance program has therefore been set up. Steve Symeth from Purdue University in the US is one of the scientists behind the project. For several months, he has been traveling around Haiti installing GPS equipment. The apparatus enables the slightest ground movements to be observed month after month. The data then provides precise and detailed maps of the deformation zones and helps to determine the speed of the plate's movement.
We set up this apparatus and leave it in place for at least 4 days, 3 or 4 days. Then we remove it and then come back every 3 or 4 months, quite regularly, to take measures to make sure we have a representative series over time. Thanks to these measurements, we can calculate variations in the strain in the crust, and this enables us to explain the aftershocks we observe after an earthquake, and also, perhaps, to anticipate other earthquakes to come.
Initial measures show deformations of around 2 centimeters per year. The slip and friction between the two plates apply colossal strain to the whole region, and it builds up as time goes by. This energy is subsequently released periodically when part of the fault gives way. It is at this point that earthquakes occur. To further improve their knowledge of the movements affecting the zone, another team has been deployed in the field. Run by Bernard Mercier de L'Épinay from the CNRS in Sophia Antipolis in France, it is entrusted with setting up a series of seismographs at strategic points in the region.
We're here next to this antenna because we've set up a seismological station to record the seismic waves. And this antenna is one among 23 that we're equipping throughout the country. We use seismic waves, which are waves like light, and which enable us to create images of the rocky milieu and to see where the main fractures are that cross it.
The seismographs measure the amplitude and direction of ground tremors in real time, even the very slightest. By analyzing the data, the scientists can make detailed models of each small fault that splits the region at the junction of the plates.
Where we are now, we're practically parallel to the direction of the plate's movement. Not completely parallel, but we're on a line we can qualify as a crust fault, which means one plate wants to go under another, and that poses a problem of deformation. You can well imagine that when two plates are face to face and one moves under the other, it creates a lot of deformation on the surface.
There is no doubt that further earthquakes will occur here. But scientists now hope to be able to see them coming and to warn the local population. Meanwhile, tectonic forces continue to shape the Haiti landscape. The slipping plates have torn the rock apart deep down, transforming the ground into a hole-filled Swiss cheese. Underground rivers and vast caves have formed everywhere. In the region of Pestel, the Belloni caves are among the best known. Emmanuel Soilik is the guide in charge of the site. He has been exploring the caves for years and reveals their secrets to visitors. Flooded on several occasions, the impressively vast caves are decorated with countless stalagmites and stalactites.
There's friction between the North American plate and the Caribbean plate. Water came in and covered the mountain. The empty space was created below. Then, as it moved out, the water created stalagmites and stalactites. And at the same time, these concretions we can see were also created by the water.
Emmanuel knows the place like the back of his hand. As a child, he loved to get lost in the rocky maze, despite the superstitions that surround it.
When I was little, I used to come here when people had voodoo ceremonies. I lived in Pestel, and I thought the Bellany Caves were the devil's hole.
Be they underground or under the sea, the numerous cavities in the Caribbean plate are one of many local treasures. For connoisseurs, the sumptuous Blue Hole off Belize, for example, has become one of the top spots for divers. For hundreds of thousands of years, Central America has constantly been redrawn by the movements of the terrestrial crust. On its eastern facade, volcanoes and earthquakes are an integral part of the Antilles' history. On the western side, a different type of event has profoundly transformed the whole region. 3 million years ago, North and South America moved closer together to the point of touching. The two continents were joined together, and a new land was formed, the Isthmus of Panama. According to the experts, it would have been formed in several successive stages. It all began about 15 million years ago. As the Pacific plate slid below the Caribbean plate, a string of volcanic islands appeared. At the same time, tectonic movements pushed parts of the seabed to the surface. Other fragments of land emerged from the waves. Then sediment built up over the millennia and gradually filled the empty spaces. Finally, the isthmus closed up completely just 3 million years ago. But at the beginning of the 20th century, man decided to counter the tectonic forces, digging a gigantic canal to link the Atlantic and Pacific Oceans as they were previously joined. This Herculean task was one of the most difficult projects ever attempted, but its impact on maritime trade is still considerable even today. New work has been underway for several months. The aim is to widen the canal to allow even bigger vessels to pass. The work represents a great opportunity for one team of scientists. Andres Cardenas is a paleontologist at the University of Los Andes in Colombia. Along with his colleagues, he comes here regularly to examine the rocks excavated by the huge diggers.
The expansion of the Panama Canal is giving us a new opportunity to look at the rocks in this location because they are creating artificial exposures. And then we could see the fresh rocks and the fresh fossils. In those environments, we could find several mammals. Some animals like the marsupials, the opossum, the armadillos, they are from South American origin. And they are, if you go today to Texas, you have that marsupials, you have the armadillos. In contrast, you have here in South America, mammals from North American origin, just like the jaguars. The mammals that we have found here are from North American affinities. It is telling us that there was a corridor from the north through South America.
When the two Americas came together, the wildlife was involved in extensive migration across the new land bridge. After evolving apart for millions of years, species from the north and south met and interbred, colonizing whole new territories. This event, known as the Great American Interchange, had a considerable impact on the biodiversity of the two continents. For Andres Cardenas, each new fossil that is discovered is a precious clue.
In the Culebra Formation, you could find marine fossils, like bivalves, oysters. It is telling us that this location was at some point under the sea, at another points above the sea.
The mix of land and marine animal fossils provides valuable information about the formation of the Panama Isthmus.
That historical event was a very drastic event because it changes not only the biological dispersion of the South and North American animals, but also it changes the global circulation pattern, and maybe could change also the climatic mode of the Earth.
A slender strip of land stretched between two continents, the Central American Isthmus, has played its part in changing the equilibrium of the whole planet. A remarkable destiny akin to that of the Caribbean plate. Born in the depths of the oceans, shaped by earthquakes and volcanoes, it was formed in barely 100 million years. A mere moment in the Earth's geological timescale. And it has given rise to landscapes of exceptional beauty. Today, the region's history is far from over. To the east, confrontation with the Atlantic Ocean will form new islands. In a few million years, they could perhaps join together and even form a new land bridge between the two Americas. At its birth, 4.6 billion years ago, the Earth is a gigantic ball of lava. Then it cools, and rocky plates aggregate, forming the first fragments of the Earth's crust. Thus begins the first chapter of the history of the North American continent. In Montreal, located in eastern Canada, it so happens there's a researcher who studies these vestiges of our planet's infancy. Professor Don Francis works in the Department of Earth and Planetary Sciences at the prestigious McGill University. Every day, he rides his bike across Montreal's historic city center to his laboratory. This area is ideal for geologists because 90% of the province of Quebec is covered by what's called a craton, a fragment of the Earth's crust which has remained unchanged for billions of years. The rocks that crop out here are not the oldest, but for the scientist, each one will likely reveal an element of North America's story nonetheless.
So all these rocks are much younger than the rocks of the craton, which normally are 2.7, and our team have discovered an area in the craton where the rocks are as old as 4.3 billion years old. This is a very old age, and the rocks there tell us a lot of interesting things about that time. For example, we know that because there are pillow lavas there, that there was an ocean. This was at a time when the moon was being bombarded by very large meteorites. All the big craters you see on the moon were produced during this time. And in fact, it must have been happening on the Earth as well. So you have a marine environment where there are hot springs and there are big meteorites falling out of the sky. So it's a very unusual environment.
Don Francis and his colleagues recently discovered these rocks dating back 4.3 billion years in northern Quebec. The announcement caused a sensation in the scientific community. These rocks are, in effect, the oldest specimens ever discovered. The study of their structure gives an unprecedented view of the environment that reigned on primitive Earth. But the geologists must still confirm the rock's age in a definitive manner. To do this, they look for traces of a particular mineral inside the granite, zircon. This mineral is known to be exceptionally stable and to contain infinitesimal quantities of uranium, which over time transform into lead. Thus, by calculating the proportions of lead and uranium in the zircon crystals, the exact age of the rock can be determined. Cut in very fine slices, the samples reveal their inner structure under the microscope's lens.
Here's one of these garnets. They're black with the filter in, but when you take the filter out, they're clear. And that's the way you identify garnet. Up until recently, 3.8 were the oldest rocks. The result of that is a lot of people are now going back to 3.8 areas, of which there are not very many. You could probably count them on two hands, maybe less. But they've been going back into these areas, trying to see whether they can find the same anomaly that we found, and to see whether there are, in fact, more than one occurrence of very old rocks.
Every day, Don teaches his students the history of the Canadian craton. Other tests are still necessary to assure that the oldest of the rocks are indeed 4.3 billion years of age.
The field trip is going to be to the Mont Region Hill.
But if the results are confirmed, a new chapter will be added to the class syllabus, that of the birth of the North American continent's very first landmass. Later, fragments of the Earth's crust spread across the surface of the globe, migrating and combining with one another. When they collided, mountains were created. When they broke apart, oceans and seas were hollowed out. Then water and rain eroded their surface over millions of years. Traces of these ancient events are still visible today, notably on the Colorado Plateau in the heart of Monument Valley. Here, successive layers of strata testify to the never-ending evolution of the relief over millions of years. but the tectonic plates are always in motion. And 500 million years ago, the continental land masses in the northern hemisphere began to draw closer. Little by little, they began to collide with Africa. And about 100 million years later, a vast supercontinent was formed, the Pangaea. Today, the landscapes tell the story of Pangaea's birth, a major event in the history of North America. Southeastern Canada, in the province of Nova Scotia, the city of Passborough is located near the Appalachians. A vast mountain range born when America and Africa collided. Paul Olson, a geologist and biologist at Columbia University in New York, knows the area by heart. He's roamed these coasts for many years in search of new clues to Pangaea's history.
This is Nova Scotia in eastern Canada. 300 million years ago, on this spot, North America and Africa collided, producing Pangaea, the last of the great supercontinents. This is really the center of the action. Let me show you with a drawing. Here's North America, and it's heading this way. And here comes Africa, and it's being shoved below North America. And when they finally collide, they produce an enormous mountain range, the Appalachians.
Sprung from the Earth 270 million years ago, today the Appalachians spread over more than 3,000 kilometers. A veritable open-air geological archive, it's the proof that long ago America and Africa formed one and the same territory.
When the North American and African plates collided, they did so with tremendous force, so much so that they shoved the rocks up from their original flat-lying positions into these twisted and contorted forms that you can see here, barely recognizable from the way they were when they were formed. And you can find exactly the same kind of rocks in Africa today. So what actually happened? At about 50 million years later, the North American and African plates began to collapse. And as they collapsed, Africa began to pull away from North America, and the crust began to stretch and sink, forming a giant rift basin, when finally the Atlantic Ocean formed about 200 million years ago.
The opening of the Atlantic Ocean marks the end of Pangaea. But this fracturing makes for a bumpy ride. As the continents break apart, the Earth itself fissures in all quarters. In the interstices, astronomical quantities of magma rise from the depths of the mantle. Massive successive volcanic eruptions continue for more than 600,000 years.
Now that rock is really interesting. On this side, you see red sediments deposited by streams and rivers. On this side, you have a completely different kind of rock. It's called basalt. It's basically hardened lava. It's 201.6 million years old. And it's vivid evidence of the formation of the Atlantic Ocean, right here. If you look carefully, you can see little white dots. Those are minerals that filled in holes that were originally filled with gases. And those gases caused a mass extinction at exactly the time of the eruptions of these lavas. One that shaped the future of life on Earth, and in fact allowed our ancestors very long ago to survive and fill the world. animals and plants were quite different in different places, and there was a tremendous amount of diversity on the land. There were crocodile relatives that were dominant in the landscape over all of Pangaea. However, when North America and Africa began to split apart, and the lava erupted in that enormous area, the gases that were produced by that eruption caused climate changes that killed off almost all of the crocodile relatives, leaving ecological space open for the dinosaurs to occupy. And after that is when dinosaurs actually took over the Earth, and we begin the real part of the age of dinosaurs.
200 million years ago, the tectonic plates resulted in a massive extinction of species.
These are interesting.
In total, half of the Earth's biological diversity disappeared, giving the dinosaurs free rein. Thus began their unrivaled dynasty on the planet. Along the banks of Nova Scotia, a few of these reptiles' fossil prints are still visible, the last remnants of their former domination. But much further inland to the west, these Cretaceous giants left other evidence of their passage. In the Canadian province of Alberta, the city of Drumheller houses the Royal Tyrrell Museum, the largest in the world dedicated to dinosaurs. Gathered here are the skeletons of hundreds of specimens representing more than 35 different species. François Terrien is a paleontologist and geologist. His specialty, the study of the environment and behavior of dinosaurs during the Cretaceous period.
So we're here in the storage room. It's here that plaster jackets containing the fossils are stored until they can be prepared. As you can see, there are a great many fossils. The oldest date back to 1962, and we'll probably never be able to prepare all of them. There are so many specimens. There's always a priority. We always prepare the nicest specimens before the others.
Hi, Donna. How are you?
Hello, I'm good. How are you?
Good, good. What you working on?
I'm working on a gar block.
Oh.
3D gar, very rare. So far I've found about 20 of them in here.
Cool. Well, I was coming to ask you, do you want to go to the field, go to the Tolman Ceratopsian dig site?
Sure.
Cool. Okay, well, I'll have a few things to do, and then I'll just meet you at the site then.
Cool.
Cool. See you there.
The Alberta region is François Terrien's main excavation zone. The great majority of fossils exhibited in the museum come from an area called the Badlands. This valley, with its almost lunar scenery, draws a long scar across the Canadian West. It formed 100 million years ago. At that time, the face of North America was vastly different from these spectacular landscapes.
About 180 million years ago, at the end of the Jurassic period, a subduction zone developed on the west coast of the North American continent. Because the crust fragments rose and pressed down on the North American, the continent started to sag, forming a huge depression in the middle of North America. Over millions of years, the marine level fluctuated in such a way that the ocean invaded the center of the North American continent, developing a great inside sea that connected the Arctic Ocean to the Gulf of Mexico. Great coastal plains rose up around this inside sea. These coastal zones were inhabited by the dinosaurs.
Buried under the sediment, the skeletons of reptiles have traversed time and reappear today in a perfectly preserved state.
Hey guys, how's it going? Good, good. Anything new? A skull or something?
Since dinosaurs only lived between 230 and 66 million years, we have to find the rocks that were deposited here during that period. So south of Alberta is the best place on Earth because it meets these criteria. There are rocky outcroppings that formed around 80 to 66 million years ago, deposited in the rivers and lakes, and we also have the advantage of a very arid climate, which limits plant growth. There are no big forests to cover the outcroppings, so there are a lot of rocky outcroppings, which means we can walk about the typical Badlands landscapes and discover other dinosaurs.
François and his colleagues delicately probe the soil, looking for the tiniest fragments of fossilized bone. And like every year, the prospects look good.
We see here, it's a bone poking out of the rock. It's the backbone of a horned dinosaur, a ceratopsia. So in fact, we can say that tectonics aren't only responsible for forming the Great Plains of the North American continent, but tectonics are also responsible for providing ideal conservation conditions for all the dinosaur bones we find here. As the rocks rose and the Earth's crust sagged, there were a lot of rivers running towards this inside sea. These rivers overflowed the plains with alluvium and buried all the animals here. And it's thanks to this tectonic phenomenon that we can admire dinosaur bones in museums all over the world.
Tirelessly, each year the researchers continue to unearth new bones. These fossils make it possible to deepen our knowledge about dinosaurs, but also of the history of the Great Plains, the swath of terrain born in the heart of North America more than 100 million years ago. But further west, the age of dinosaurs is marked by another major geological phenomenon. The continent drifts slowly, colliding with fragments of the continental crust dispersed across the ocean surface. These tiny islets of land successively graft themselves to the North American plate, which grows little by little. This is how the four most westerly states on the continent, Nevada, Oregon, California, and Washington, were formed. Alan Glasner, geologist at the University of California, studies the history of these collisions that gave North America its final shape. He carries out his research in the heart of Yosemite National Park. With its mountains, lakes, and waterfalls that hurtle down the slopes, it's one of the most beautiful parks in all of the United States. The result of the encounter between North America and the future Western states. The collisions caused a folding of the rock and provoked violent volcanic eruptions. Magma rose from the depths, and as it cooled, formed these gigantic granite domes.
If you looked at Western North America from space before Pangea broke up, it would have looked quite different. Much of today's Nevada, Oregon, Washington, California would have been underwater. But as subduction started,
As North America moved westward, then suddenly the continent started to grow because you started adding things like the granite we're standing on. And if you look at it carefully, you can see lots of detail in it that shows you how different pockets of magma came up and cooled and crystallized to form this body here. And one of the most obvious examples of that are these late dikes that came in. As the magma cools, as it gets almost 100% crystallized, it cracks, and the very last liquid gets sucked into those cracks to form these beautiful dikes that show up so well on this glaciated surface.
These veins of rock, which scientists call dikes, are proof of intensive volcanic activity in the past.
So on the map, we've mapped out all these different pulses. Some of them are dark colored, some are very light colored stripes, and they allow us to work out a sequence of injections of magma into this area.
Magma from the Earth's depths has thus infiltrated fissures in the rock to reach the surface. There was a time in history when Yosemite National Park, like the rest of the American West, was in fact located off the coast in the middle of the Pacific Ocean. But when pieces of the Earth's crust collided, they finished by melding into a single continent. Around these collisions, the Earth gave rise to California's highest mountain range, the Sierra Nevadas, which stretch more than 700 kilometers from north to south. In the field, Alan Glasner constantly analyzes clues to these past events to recover the details of the region's geological history. Today, he is joined by one of his students at the foot of the park's most famous monolith, El Capitan. Here, the granite cliff rises more than a kilometer high.
Roger, how's it going?
Going well. Yeah, check this out, Alan. Here's a piece of that apatite. What's the black? Biotite?
Yeah, all I can identify is biotite. That's a pretty rock.
Yeah.
We should definitely get a sample to analyze if it isn't in your database already.
Yeah, I don't have it from specifically here yet, so yeah, let's get one. I think one of the coolest pieces about the geology of El Capitan is that where we are right here at the base of El Cap was 10 kilometers below the Earth's surface 104 million years ago, which is the same time as dinosaurs were roaming the Earth. So 10 kilometers above where we are now, there were dinosaurs walking around, which is just one of the coolest things.
And there were big volcanoes going off at the same time, so those dinosaurs had a lot to worry about.
Today, the Sierra Nevada's highest summit reaches an altitude of 4,400 meters. But this height pales in comparison to the colossal mountain that stood here in the past. Because over millions of years, water, wind, and ice have worn down the rock. From the summit of Half Dome, Alan can contemplate the effects of this slow erosion. The Sierra Nevadas are now composed of a series of valleys and mountains with rounded peaks.
When the Sierra Nevada formed, say 90 million years, and we're sitting here, you'd be about 10 kilometers down in the crust. There would be a very tall chain of volcanoes above you, and there would be a subduction zone being subducted about the normal angle of the plate was going down. It may be 45 degrees. I'll make a sketch to illustrate that better. When the subducted plate gets to a depth of about 100 kilometers, then chemical reactions occur that produce magma. And so this magma rises, being less dense, gets to the surface, it piles up and erupts, forms volcanoes and lava flows. It erupts volcanic ash, and some of that magma gets trapped in the crust at depths of, well, let's say 10 to 20 kilometers. And when it cools and hardens, it forms granite. And that's what we're standing in here. Erosion has taken off the upper layers of the crust, and we're down within this magma factory.
The Sierra Nevadas, with its sumptuous landscapes, is one of the places that best demonstrates the constant evolution of the continents. It was here, 100 million years ago, that North America extended westward to take on its current form. But during the same period, a different phenomenon was taking place a bit farther east. Another mountain range was also rising from the earth, the Rockies. This massif stretches for more than 4,800 kilometers from New Mexico all the way to northern British Columbia. The Rocky Mountains formed during the same period as the Sierra Nevadas, but for a long time, they mystified geologists the world over. Generally, mountain ranges are born at the edges of colliding plates. How then do we explain the presence of these peaks nearly 1,000 kilometers inland? Today, a hypothesis is at last taking shape. About 80 million years ago, a plate slid under the North American continent, but instead of dropping down at a 45-degree angle, as is usually the case, it wove its way in much closer to the surface. As a result, the rock didn't reach a sufficient depth to be melted by the heat. So the plate continued its journey, and jamming against the Earth's crust in its path, gave rise to the Rocky Mountains. Today, not every detail of this event has been perfectly elucidated. But in all likelihood, the origin of the Rockies is a geological anomaly, a willful plate that suddenly refused to submerge. Backed up against the Rocky Mountains, another region was victim to the Earth's fitful rage for thousands of years. Yellowstone National Park, located in the state of Wyoming. Henry Heelsler is the park's geologist. Every day he roams this immense natural reserve. His mission, watch over the monster that sleeps just beneath the surface, a supervolcano of unimaginable strength. For years, specialists have tried to understand the origin of this supervolcano. They finally discovered that Yellowstone Park is situated on what is called a hotspot. These are zones where under the surface, the base temperature is unusually high. Thus, enormous quantities of magma rise from the depths and accumulate in a pocket several hundred kilometers under the ground called a plume. When the magma is expelled, it pierces the Earth's crust and a volcano appears. But when the tectonic plate slowly floats above it, the hotspot doesn't move. It thus imprints its mark at regular intervals along the Earth's surface. In the last 2 billion years, the Yellowstone region was the site of 3 major eruptions. The last one dates back 642,000 years. Accumulated beneath the Earth's crust, the lava burst from its chamber and projected thousands of tons of molten rock, volcanic ash, and sulfurous gases into the air.
When material is forcefully erupted, not as a big blast, but basically vented through all the fissures and cracks that were forming in the earth, it forms a caldera, which is a subsidence feature, and behind me you can see the evidence for that. Basically, the caldera starts almost exactly where I'm standing and then goes 72 kilometers directly behind me, where it's covered by more recent lava flows.
In the heart of the national park, the Yellowstone caldera forms a gigantic basin 72 kilometers long by 56 kilometers wide. It's all that remains of this colossal explosion, one of the most devastating in the history of the Earth. But today, the supervolcano is far from extinct. The Earth here rumbles non-stop. Geysers, gas, and vapors, as well as other heat sources, punctuate the landscape, evidence of the intense activity that reigns beneath the surface. The volcano is simply dozing, and it's potentially one of the most destructive on the planet.
The super eruptions of Yellowstone, catastrophic for hundreds of kilometers around what currently is Yellowstone National Park. There would be no life left because of the force of the eruptions, the pyroclastic, the hot rock flows that come out tens of kilometers, the resulting ash clouds, the volcanic ash and volcanic gases that would be ejected high into the atmosphere and basically circle the entire globe would cause a volcanic winter to cover the entire world.
For many years, Yellowstone's supervolcano has been under close observation. The control center is located about 500 kilometers from there at the University of Utah in Salt Lake City. Jamie Farrell is a geologist. Every day his task is to analyze the volcano's slightest flutter, thanks to a network of sensors that measures deformations of the ground in real time. Recently, he also recreated the monster's history and constructed a model of the vast magma chamber that feeds it.
So this is just a visualization tool that we use to kind of show the data that we record in Yellowstone. If you turn off the topography and we want to put on the earthquakes that we recorded in Yellowstone as these red dots, what you can do here, you can zoom around and look underneath the ground and look at the patterns of earthquakes that have occurred from 1973 to the present. And again, there's roughly about 46,000 earthquakes here. If you want to look at a little bit of the bigger picture, we can turn on the Yellowstone plume, and that's this orangish yellowish feature here. This is basically the Yellowstone hotspot. This is the feature that's providing all the heat and energy coming up from the mantle to feed the Yellowstone volcanoes. So you can see here it comes down into the mantle. So the Yellowstone hotspot manifests itself on the surface about 16 or 17 million years ago down in this area down here in the Nevada, Oregon. So this is kind of the track of the Yellowstone hotspot as the North American plate has moved over it. The western U.S. is stretching. We have an area called the Basin and Range where the crust is being thinned and stretched. The reason why the Yellowstone hotspot is here is because of that thinning, and that may have provided a path for the hotspot to make it to the surface.
Some 3,000 low-magnitude tremors shake the Yellowstone region every year. The earth trembles, the ground is deformed, the composition of the gases evolves. But in the eyes of specialists, there is, for the moment, no proof of an imminent eruption.
Change is the normal situation at Yellowstone with earthquakes, with ground deformation, with the geothermal system, with the gases. So roughly, the probability of another catastrophic eruption is very poorly understood because we've only had 3 in the past 2 million years, but it's about the same as a large asteroid hitting the Earth and destroying it. So if you're concerned about a large asteroid hitting the Earth, then maybe you should be concerned about Yellowstone having a catastrophic eruption. The future of this volcano eventually is to become very, very cold and inactive. It will probably end with outpouring of basalts. The ground elevation will go down because it will no longer be very hot, so we'll have a very, very different looking terrain sometime into the future. It may be millions of years into the future. So the more interesting question for me is, will humanity even be around when Yellowstone changes a lot?
One day, the supervolcano will thus disappear. Until then, the volcanic gases of this hugely powerful monster will continue to dance above the staggering beauty of these lands. But today, another large-scale phenomenon is in progress. An immense scar rips through the western region of North America. Baptized the San Andreas Fault, it runs for 1,300 kilometers through California. In this area, the Pacific Plate climbs northeast, while the North American Plate descends in the opposite direction. The result? These two fragments of the Earth's crust slide against one another, making the ground tremble at regular intervals. On the banks of the San Francisco Bay, specialists from the University of California keep careful watch over the San Andreas Fault 7 days a week, 24 hours a day. Everyone here is used to the regular tremors produced by the Earth's movements. The fault line is part of everyday life for Californians. On the campus, geologist Roland Bergman teaches about the history of geology, but also of its future. Because inexorably, California is breaking off from the continent at a rate of 5 centimeters a year. In a million years, it will have become an island.
The San Andreas Fault was born about 25 million years ago. Before that time, California was a place where subduction occurred. So the San Andreas Fault is a strike-slip fault. That means that motions of plugs or plates adjacent to the fault are parallel to the fault and horizontal in a strike-slip motion, rather than one plate moving on top of the other, as we might see in a subduction zone. And if we have the San Andreas Fault continue with its motion, and there's no reason to believe that it would stop, in another 9 million years, we should be seeing the Los Angeles basin offshore here and ruining our views.
A squeaky valve between two plates of the Earth's crust, the San Andreas Fault gave birth to a complex system of fissures. Several secondary fault lines have appeared and now run across the entire region. Among them, the Hayward Fault, which runs to the east, is particularly worrisome to seismologists. Aurélie Guillem is a postdoctoral candidate from France at the University of California at Berkeley. In the field, she's on the lookout for possible signs of movement along the Hayward Fault.
So here we are in the city of Hayward, which has the same name as the Hayward Fault. It was here that the 1868 earthquake took place. In addition to powerful earthquakes of a magnitude of about 7 that occur along this fault, the fault also causes slow slipping. We can observe this slow slipping on the sidewalks, like here, but also by the cracks along the streets. This sidewalk wasn't made like this. It was built straight, but since then has been deformed by the fault zone that runs through here. We can clearly see the movement in the relationship between these two blocks. This movement corresponds to the movement of the Hayward Fault, which has a right lateral strike slip, so the block propagates to the south in relation to this block here, which propagates to the north.
The plates thus slide slowly against one another. But sometimes the accumulated energy suddenly cracks the fault. It ruptures, provoking an earthquake.
We're at the Memorial Stadium on the Berkeley campus. This stadium was built in 1923, after the 1868 quake hit along the Hayward Fault. It measured 6.8 on the Richter scale. This stadium was built after that, and it has some deformation that can be seen on the top of the stadium here, where in fact the Hayward Fault cuts the stadium in two. So it's been affected over time, even since the structure was built. Deformation is about 40 centimeters, and it proves that the Hayward Fault slides continuously about 0.5 centimeters per year. It's a relatively new structure, but we can clearly see a large deformation with the naked eye.
April 18, 1906, another earthquake registering 8.2 on the Richter scale hit the city of San Francisco. There were 3,000 victims, and it transformed the city into a vast field of ruins. This same phenomenon took place on October 17, 1989. 63 people died, nearly 4,000 others were wounded, and material damage reached almost $6 billion. Today, what everyone fears is the big one, the megathrust earthquake that's supposed to hit California in the next 30 years. For Richard Allen, director of UC Berkeley's Seismological Laboratory, residents must definitely prepare for this disaster scenario.
So here we're on the UC Berkeley campus, and the Hayward Fault actually goes across the Berkeley campus. So if we have an earthquake on that fault, then we expect fairly significant damage in this area. Most of the buildings on campus here have been retrofit so that they should not collapse during an earthquake. However, many may be seriously damaged, and we won't be able to use them following the event. So while we can't predict the exact time at which an earthquake is going to occur, we know that we're going to have big earthquakes in this region over the next few decades. In fact, it's about a 2 in 3 chance of a major damaging earthquake in the Bay Area in the next 30 years. So that's how we can then get ready for these earthquakes, by building buildings. But the other thing that we can do is we can use the very beginnings of an earthquake, the P waves that radiate from a fault, to say something about the shaking that's coming and provide a few seconds warning to people before they feel the shaking.
Will the famous Golden Gate Bridge stand up to the big one when it hits? One thing is certain, the population must prepare itself for the next tragedy. Aurélie Guillaume studied the possible consequences of a megaquake in the San Francisco Bay Area. And it's from this promontory overlooking the bay that the amplitude of potential damage is most visible.
From here, we can get an overview of the Hayward Fault. So behind the hill is Berkeley with the Memorial Stadium. In front of us is San Francisco, and right there is Oakland. During a future quake, the Hayward Fault will break at this spot here with serious consequences. Below us, there's a big highway network. The Hayward Fault will cut the highway in two. This region is also very populated. And facing us, there's a gas factory right next to the fault. We imagine there'll be problems with electricity distribution in the weeks following a future quake. Something else that can't be seen here are water pipelines in that area, running east to west and thus crossing the fault line.
During the 1906 earthquake, broken water mains prevented firemen from putting out dozens of fires that ravaged the city.
If the water lines here are blocked or shut down, as well as the highways, and the electricity is out, we are looking at a pretty big natural disaster in this highly populated region.
Every day, experts are on the lookout for the slightest tremor, ready to sound the alert in the case of an imminent quake. But until then, San Francisco keeps its cool. As if the all-powerful tectonic forces couldn't mar one of the most beautiful cities in the world. North America as we know it today represents only an ephemeral stage in the planet's history. In the future, the Earth's terrible fits will continue to mold its landscape. Earthquakes and volcanic eruptions threaten one day to wreak long-lasting consequences on the entirety of the living world. And in several million years, the continent will be ripped in two. California will detach and drift at length through the Pacific Ocean. The colossal forces of the tectonic plates have not yet finished sculpting the surface of the North American continent. When it was born some 4.6 billion years ago, our planet was a gigantic ball of fire. Then it cooled, giving way to the first oceans and the first embryonic continents. As time passed, the emerging land masses came closer together, forming vast islands of terrestrial crust. 2 billion years ago, one of these continental masses, known as the Amazonian craton, became the cornerstone of the future South America. Nelson Rice works for the Brazilian Geology Service and is one of the leading experts on the history of the Amazonian craton. He's working in the north of Brazil, in the Tiepecem region. It is here that the last vestiges of this original land can be found, remaining unchanged since they were created. He explores the region relentlessly, looking for rocks that were part of the craton. It's a delicate mission, as the elements have changed the landscape over millions of years. Ancestral lands lie on the slopes of mountains with flattened tops that the Indians call tepuis. For Nelson Rice, these rocky peaks provide valuable testimony for a better understanding of the origins of the South American continent. Over time, the Amazonian craton moved on the Earth's surface and collided with other landmasses. 1.8 million years ago, it was trapped within the vise of a supercontinent, Columbia.
To reconstruct the story of the Columbia supercontinent, we need to do field studies. This involves collecting rocks for dating and studying what we call paleomagnetism. The data enables us to know the age of the rocks in question and also where they were situated in relation to the Earth's magnetic pole at the moment they were formed.
In recent years, Nelson Rice and his colleagues have collected and analyzed hundreds of samples. The results reveal a particularly complex puzzle.
Here in South America, we can observe at least 4 cycles of supercontinent formation. The oldest led to the formation of the supercontinent Columbia, followed by Rodinia, then Gondwana, and the youngest of them, in the Mesozoic, the Pangaea.
For millions of years, through tectonic plate movements, the future South America was therefore at the center of various differently shaped supercontinents. Today, the history of these successive assemblies is still little known. The surface of the planet has retained little evidence of these extremely ancient events. But at the University of Tucson in Arizona, one rather adventurous geologist has decided to investigate in order to reconstruct the various phases in the evolution of South America. He is Martin Bailey Pepper, a geologist and a motorbike fanatic. For several years, he has been exploring South America by bike, collecting unusual samples. Zircon, a mineral present in sand grains with the quality of being extremely stable.
What I really love about geology is that you can pick up just, let's say, a handful of sand here. And as a geologist, using the right tools, you can get in and just look at a single grain like a zircon. And you can take that single grain and you can zoom into that and get a whole story of not only when this formed, but you can go back farther, what fluids were there before this formed. You can also go forward and figure out so much information about the time it took to slowly come out of the deep mantle as these rivers removed more and more off the top of these mountains, bringing this up from hundreds of kilometers deep, finally getting it to the surface. There's so much information into one of these grains of sand. And yet, that's almost the biggest thing we have when we go back billions of years to figure out what happened to things in Rodinia, or farther back to Columbia, or farther back to the beginning of the Earth itself.
Martin has already covered some 50,000 kilometers, from Patagonia to Ecuador. He's collected more than 8,000 samples from almost every river across the continent.
And so all I had to do was go into these river valleys with a gold pan, separate all the light minerals that I didn't want, and take just the zircon home. And it was those zircons that I could then take into our lab and analyze.
Back in his laboratory in Tucson, each grain of sand is washed, filtered, then analyzed using a laser. This process provides the precise age and composition of each grain of zircon. Martin hopes he will soon be able to identify the origin of all the sediment, and thus retrace the geological history of Latin America over 3 billion years. There are still years of work to be done, but already the first results are promising. The geologist has discovered grains of sand from every part of the continent that are some 900 million years old. This would suggest that at the time, all the fragments of land that make up South America were all assembled together.
When I think of the Earth, I like to envision it as almost like when you're cooking hot cocoa. And so you have the heat underneath the pot, and that causes this upwelling current, this convection cell. And the continents are really just these little marshmallow bits that float around on all that convecting magma. On Earth, as we know it, we see these giant continents. But when you go back in time, a continent is composed of these stabilized blocks. And it's these blocks that will actually separate and collide in time. And scientists have discovered that these blocks separate and coalesce into these supercontinents about every 400 to 500 million years. And these blocks can completely disassociate from what we understand as North America, South America, Europe, Asia, Africa. And so when we go to the time of Rodinia, the final assembly about 900 million years ago, many of these continental blocks that we would think of associated with South America look completely different. They were kind of in the middle of this supercontinent, but they were separated. And so after 900 million years ago, as all these blocks started to be ripped apart, we then disassociated with something we wouldn't even recognize. And then they started to coalesce into something that we could finally say, ha-ha, that looks just like South America.
900 million years ago, the dislocation of a supercontinent would therefore have given rise to the future South America. The pieces of terrestrial crust that compose it began a long, common existence, and nothing would separate them. But subsequently, the continent would experience other dramatic changes. About 700 million years ago, the land masses of the southern hemisphere converged, and the future South America collided with the future Africa. This contact led to the appearance of a new supercontinent, Gondwana. The land today can tell the story of the birth of Gondwana, a major episode in South American history. We're in Rio de Janeiro, Brazil's second biggest city. There's a laboratory here with a very evocative name, the Gondwana Lab. It was founded by Renata Schmidt. Her objective is to understand every detail of every step in the formation of Gondwana. A century ago, it was the first supercontinent to be recognized as such by the specialists. It confirmed the hypothesis of the existence of plate tectonics.
It's like a perfect puzzle which fits together. So this was actually a very strong evidence for building up the theory of the continental wandering. This was in the 1920, more or less, and it evolved in 1950, 1960 to the theory of the tectonic plates. And it's just evolved much faster after the 60s because of all the knowledge we got from the oceans, because we didn't have access until the 50s. until the Cold War. In the Cold War, they started to build up submarines, and now they started to study all the oceans of Earth, and then we started to get better information, and then we understand that the continents actually are tectonic plates that move along the history of Earth since the beginning until today. The origin of Gondwana, the word Gondwana, comes from the 19th century when they found in India, in a region in India, Jaipur, and this region, there was this people, they call the Gonds. It's like an Aboriginal people. And they found there a sequence of sedimentary rocks of the Carboniferous period. And within these rocks, they found fossils of Glossopteris, which is a kind of plant. And the same sequence, the same flora they found in Antarctica, they found in the basins of Africa, and they found also in South America and in Australia. This is weird, like how can a plant travel from all this very large distance? So these continental masses should be together at some part of the history of Earth. And of course, another very strong evidence of the Gondwana amalgamation and the Gondwana existence is the fit of the continental margin.
For several years, Renata Schmidt and her colleagues have been studying the rocks of South America to learn more about the history of the supercontinent. Claudio Valeriano, a geologist at the University of Rio de Janeiro, is particularly interested in the famous Sugarloaf Mountain, which stands majestically over the bay. This granite mountain, rising up 395 meters, is the result of a violent collision between tectonic plates.
This is a peculiar shaped rock that was eroded from a granite, a kind of granite that formed when some old continental blocks collided about 600 million years ago. The Sugarloaf is just an erosion form which was formed much later when Africa and South America broke apart.
When they collided, the rocks of the future African and South American continents folded and fractured. Magma rose to the surface, and gigantic mountain ranges emerged from the ground. Erosion then took over, and the granite peaks that dominate the Rio Bay today are all that remain of the monumental age-old relief. After 300 million years of coexistence, Africa and South America separated. It was a brutal dislocation, traces of which are still visible in the very heart of the rock.
We have here in Rio de Janeiro some rocks that testify this separation, which are the dolerite dikes. These are black rocks that fill fractures that were created about 130 million years ago. So these rocks, which we call dolerites, they filled these fractures, and they can be seen all around here and in the Sugarloaf area also.
Today, the Sugarloaf and the Corcovado are the best-known vestiges of that ancient collision. On the latter's summit stands the imposing statue of Christ the Redeemer, symbol of the city and indeed of the whole country. On the other side of the Atlantic, the coasts of Africa have also conserved traces of Gondwana's existence. In Namibia, the town of Keetmanshoop is in the heart of the Karus region. The landscape here was formed by the encounter between South America and Africa. As far as the eye can see, gigantic blocks of rock emerge from the plain. This breathtaking setting is where geologist Nicole Ulrich is hard at work.
This view now with the dune, I like this.
These rocks are strikingly similar to those found along the Brazilian coast.
Rocks that we see here in this beautiful valley give us evidence of plate tectonic processes. You do find similar rocks with a similar age on the other side of the Atlantic Ocean in Brazil. Like for instance, the world-known sugar loaf in Rio de Janeiro is built up by similar rocks. This proves that the two continents, which are now separated by thousands of kilometers of ocean, have once been connected together, and only later, after the breakup of the Gondwana continent, were separated again.
When Gondwana broke apart, a vast ocean gradually opened up between the future Africa and South America, the Atlantic Ocean as we know it today. But this brutal dislocation made the Earth's crust fragile, and in places it was torn apart. Magma rose from the depths and seeped through cracks in the rock. Today, these lava inclusions are visible on Namibian soil and on the Brazilian coast. They form rather unusual seams called dolerite dikes. It is these rocks that Nicole Ulrich is researching and analyzing all along the Namibian coast.
Also in South Namibia, we can find evidence of the Gondwana separation. What you can see here are dolerite dikes. They occur in such great numbers that one cannot distinguish a single dike anymore, and this is why the geologists speak of a dolerite swarm. Dolerite is a magmatic rock that, compared to basalt, which flows out as a lava on the surface, does not reach the Earth's surface, but cools off in the Earth's crust and forms long extending dikes.
Over thousands of years, erosion has brought the dikes to the surface. Today, they rise up towards the skies like rocky icebergs in the middle of the steppe. They remind us that Africa and South America were once brutally broken apart. After the separation, the South American continent began a long, solitary journey. It drifted slowly to the west, pushed by tectonic forces. But as it progressed, it encountered the gigantic Pacific Ocean plate. This new collision was not without consequences. Along the whole western face of South America, huge mountains rose from the earth. It was the birth of the Andes. Stretching over 7,000 kilometers from Venezuela to Chile, the Andes form the longest mountain range on the planet. They mark out the precise zone where the plates collided some 100 million years ago. It is in the central part, straddling Peru, Chile, and Bolivia, that the range is the most imposing. It is over 6,000 meters high and 1,700 kilometers long. It is also the focus of attention for Thierry Sempere, a geologist from the Earth Sciences Institute in Grenoble in France. He is heading for Tacna in the extreme south of Peru to retrace the region's geological history in as a detailed manner as possible. The land here has been stripped bare by centuries of erosion. For Thierry, the thousands of overlying strata are like the pages of a history book, an open-air geological archive.
So here we have some of the strata. As you can see, it's markedly stratified, with sediments deposited on a seabed. The sediments are very fine, very well stratified on the bed of a sea at least 1,000 meters deep. We're at an altitude of 2,000 meters, and so we can see that well before the Andes existed, we were in fact in an oceanic trench.
For a long time, the subduction of the Andes posed a problem for geologists. How did such marine sediments end up at an altitude of 2,000 meters? And above all, in what way could such high mountains be formed along a continent's border with an ocean?
It's true that most mountain ranges that have been studied in the past result from collisions like the Alps, the Himalayas, and others. Here, that's not at all the case. Throughout the region, the strata have not been deformed very much. They're like I'm doing with my hands, with a few undulations, but there are no folds, which would be like this. In the Alps, there are folds and thrust faults, and ancient rock that covers more recent rock, and in this part of the Andes, in the western part, we don't see that.
Most mountain ranges on the planet were created by the coming together of two continental plates. The Andes result from a very different phenomenon.
Everyone knows that the Earth is a ball, a sphere that's not exactly spherical, but almost. In its center is what we call the core, which is composed of iron, mostly in liquid form. Around the core is a kind of pulp called the mantle, and this mantle is covered over several tens of kilometers by a crust. In fact, the crust floats on the mantle, so the crust is subjected to Archimedes' principle. This means that the thicker it gets, the more it rises up, and that creates mountains. When the crust thickens, there's a substantial part we don't see beneath us, a bit like an iceberg, and there's a part that rises. And it rises at least 3 kilometers. These 3,000 meters that we've gained here are 3,000 meters that were produced by the thickening of the crust beneath our feet. And that thickening, with a rough calculation, would be around 20 kilometers.
In fact, the South American plate came into direct contact with the Pacific plate. As the latter was denser, it slid into the depths of the mantle. But the sediments that had accumulated on the ocean floor remained on the surface and were deposited along the junction of the two plates. This phenomenon led to the thickening of the continental crust, which then gradually rose. In the Andes, this terrestrial crust is now more than 70 kilometers thick in places, almost twice its normal depth. In the continent's extreme south, in the region of Torres del Paine in Patagonia, the Andes landscape is very different. Majestic peaks rise above deep valleys. The relief is chaotic, and the rock is a brownish color, its intensity contrasting with the hues of the northern Andes. The stories of the Andes formation here is more recent, and above all, much more complex. As it traveled to the west, the South American continent first of all encountered the Pacific plate. But a few tens of million years later, the southern tip found itself in a tight spot, where the Pacific and Antarctic plates were already face to face. The Earth's crust was therefore compressed, and vast quantities of magma rose to the surface. These infiltrations considerably raised the temperature of the surrounding rock, giving them this very particular color. The eternal voyage of the plates on the Earth's surface continues to change the face of Latin America even today. The continent continues to drift slowly westward, and its confrontation with the Pacific Ocean regularly causes the Earth to shake and move along the coast. This is notably the case in the region of Ilo in southern Peru. For several years, this small coastal town and the surrounding area have been carefully monitored by a team of scientists. Anne Sauquet is a geologist with the Earth Sciences Institute in Grenoble and works in collaboration with the Peruvian Geology Institute. She is studying the movements of the Earth's crust thanks to a vast network of sensors installed along the coast. Today, she is on her way to inspect one of the GPS stations with a colleague, Nathalie Cotte.
Here we are. This is the GPS antenna. So on this side at Playa Meca, we've set up a relay next to this house, which is under surveillance, so there's no risk for the equipment. The fact of having a station on the rocks is really good, to be sure that the type of readings we get are actually measuring the movements of the Earth's crust itself, and not just a superficial landslide or something that has nothing to do with what's happening with the subduction underground.
The antenna is linked to a GPS station, which picks up the ground movement data in real time. This is then safely guarded in a local fisherman's home.
Hello, sir. Hi, how are you?
Hello. Welcome to my home.
Thank you. Where's the station now? Here it is. Thank you, sir. Thanks very much. So let's take a look inside.
The apparatus is located just above the subduction zone, where the Pacific plate slides under the South American continent. The slightest movement, even minute, can therefore provide the geologists with valuable information.
The aim, in fact, is to look at the deformation generated by this subduction. The subduction involves a fault, which is blocked between two earthquakes, so it can generate huge quakes, megaquakes of a magnitude of 8 or even 9. Between two quakes, it's blocked in what we call the interseismic phase. During this phase, it's very important to measure the deformation. And I think here on this coast, we should have deformation of around 2 centimeters per year. So in fact, during the interseismic phase, the coast is moving towards the Andes Mountains. And during the coseismic phase, there's an elastic rebound, and we'll see a sudden displacement of around 5 meters, sometimes more. So we'll collect the data.
Between earthquakes, energy builds up in the depths of the Earth until it is released. But even today, predicting seismic events is an inexact science. Experts can't give a precise date for the next earthquake. But one day, they are certain the ground will shake again along the Peruvian coast. At the same time, more than 100 kilometers from the coast, Anne Sauquet and her team are studying another phenomenon. The subduction of the Pacific plate has created countless volcanoes here. Many of them are still active today and pour out torrents of lava at regular intervals. The town of Candarave in southern Peru lives constantly under the threat of the volcano Yucamane, which rises up some 5,500 meters.
This volcano is actually still active, and there's no doubt it presents quite a considerable risk for the town of Candarave, which is just below it.
Like all the volcanoes here in southern Peru.
There's a subduction zone with volcanoes behind it, except in a few places, so it's all part of the Pacific Ring of Fire. Why do we call it the Pacific Ring of Fire? It's because the Pacific is completely surrounded by subductions, and there are volcanoes all around the Pacific. But with these subductions, what they do, in fact, is make the oceanic plates disappear. So gradually, as they make the oceanic plates disappear, the Pacific will end up by closing. And as a result,
North America and South America will come and join Japan and the Philippines, etc. And so the Pacific will disappear. It will be a new Pangea.
This theory concerning the disappearance of the Pacific in a few million years is a controversial hypothesis within the scientific community. But for the moment, the Pacific Ocean continues to be slowly swallowed up in the depths of the Earth's mantle. All along the Andes, the encounter of the plates makes the ground quake and the volcanoes rumble. On the way back, Ansoke and her colleagues stop off a few kilometers from the coast. Once again, an analysis of the ground demonstrates that subduction is still going on. At this precise point, the ocean floor dives beneath the continental plate, and sediment has built up over the millennia.
In fact, about 40 kilometers beneath our feet, there's a subduction zone which generates earthquakes. But it doesn't just generate earthquakes, it also participates in raising up the Andes. We're very close to the coast here, and what we can see are different layers of different types of sediment. And when we take a closer look at these sediments, we'll see that there are shells, which were deposited by the sea. And here we're several tens, if not several hundreds of meters above sea level. So this shows that the subduction zone constantly generates deformation, and this constant deformation plays a part in raising up the coast. Perhaps we can go and take a closer look at these deposits? Have you seen it? It's really thick. It's more than 50 centimeters. Yes, so you can see here, there are lots of shells, mostly bivalves. These deposits are quite recent in geological terms, between a few tens and a few 100,000 years. So the sea was here tens or hundreds of thousands of years ago. What's pretty here, in northern Chile and southern Peru, is that all along the coast, we can see the uplift, like this. There's a kind of coastal escarpment all along the coast in northern Chile, which continues here in southern Peru. This coastal escarpment can be several hundred meters high, and in some places, it's even a kilometer high. So that's quite considerable. And it shows that there was substantial uplift here, up to 1 kilometer in the past 3 million years. So this is associated with the subduction, and we really have considerable interaction between the Great Subduction Fault, which passes beneath our feet, and the coastal morphology and the beginning of the Andes deformation. Great, we've got a 10,000-year-old scallop.
A little further north, the geological history of the Andes is marked by another rather peculiar phenomenon. In the central sector, at an altitude of 4,000 meters, a vast plain has formed in the heart of the mountains. This is the Altiplano, the world's second highest plateau after the one in Tibet. We meet up again with geologist Thierry Sempere, who's continuing his research into the region's history. He comes regularly to the shores of Lake Titicaca, on the border between Bolivia and Peru, to study the origin and evolution of this unique ecosystem. Around a picnic, he explains some of the background to his young colleagues.
Do you know the twin or the species that's the closest cousin to the tomato?
No.
It's the potato. Because when the Andes rose up, the two species diverged. The tomato stayed lower down, and the potato adapted to the altitude. And it also invented a new strategy for reproducing, which is the tuber, which is actually a clone. Because it's cold on the Altiplano at night, and especially in winter, and in case the plant might die of cold, the tuber is always in the ground and can grow again. So that's one example of many throughout the world, and so when you form mountain ranges, you create whole new ecosystems.
Located 3,812 meters above sea level, Lake Titicaca is one of the highest navigable lakes in the world. It's in the heart of the Altiplano, trapped between two mountain ranges. Thierry Sampere and his team crisscross the region, taking extensive rock samples. For it's in the depths of the Earth's crust that can be found precious indications to the formation of this high plateau.
Oh, that's not bad. And there should be quite a lot of information inside if we can get the grains out, which will help to date it. On the Altiplano, the lowest regions are occupied by lakes because the Altiplano is a sort of closed basin. The rain that falls on the Altiplano doesn't go to either the Pacific or the Atlantic, but to the lakes that are scattered around the Altiplano. The biggest of them is Lake Titicaca, which is in the lowest region in this part of the Altiplano. What we have to understand, too, is that when we go down, beneath my feet, for example, after 10 kilometers down, maybe 10 or 12 kilometers down, the Earth's crust is fragile and cracks on the surface. But after that depth, it becomes soft and plastic. We say that it's ductile, and so, consequently, it behaves like plasticine, and it spreads out. It spreads out, and so as a result, the surface of the crust we're standing on naturally becomes flatter. The relief becomes less steep because we're on a kind of mattress, a mattress made up of 50 kilometers of plastic crust.
The Central Andes were in reality formed in several stages. When the Pacific Plate dips beneath the South American Plate, it raises up the continental crust, which is gradually deformed. An initial mountain range rises from the ground, the Eastern Andes. Then along the edge of the South American Plate, subduction heats up the terrestrial crust to the point of melting it. This fluid and malleable terrain enables the Altiplano to form and rise over millions of years. Later on, intense volcanic activity causes the uplift of a second mountain range, the Western Andes. The Altiplano is therefore now locked in on the western side.
We can clearly see behind me these very flat plains where people have settled. We have the water of Titicaca, and it's all surrounded by mountains which are not very high, quite flat, we might say. And right in the background, you can no doubt see the Eastern Andes. And you have to imagine that behind those snow-capped summits, we go very quickly down towards Amazonia, towards the Amazon forest.
The majestic landscapes of the Altiplano and the Andes Mountains demonstrate to what extent tectonic forces model and shape the land's destiny. But in turn, these mountains impose a considerable influence over the surrounding regions, and in particular, over the Amazonian forest. The small town of Continental in Peru is in the heart of the Amazon basin. It is here that a team of French paleontologists has set up their base camp. Every morning, the scientists respect the same ritual, a 30-minute boat ride before setting off into the jungle on foot. The team leader is Pierre-Olivier Antoine from the Evolutionary Science Institute in Montpellier in France. He's been exploring Western Amazonia for a number of years, studying the exceptional biodiversity here. With an area of over 6 million square kilometers, this tropical forest is the vastest and most diverse on the planet. Experts say it is home to 1.4 million species of plants and animals, half of all the species so far recorded around the world. On the ground, Pierre-Olivier analyzes sediment strata to see how the watercourse has evolved over time.
This is an extremely interesting site, which is unusual for the large variety of environments concerning the deposits we've noted. Here we have a first river coming in, which has very little energy. It would have been very calm, with just a few ripples. And then the energy level goes down further, and we basically find a marshland, a marsh with animals and plants that are typical of a marshland. And then quite suddenly, the energy changes, and there's a watercourse coming in with quite a strong current. So there we have a lot of detritus laid down, with larger elements forming a conglomerate. This lasts for about 2 meters, and above those 2 meters we actually have a torrent, with large rocks washed along it, like this, so there was a very strong current. This current required relief, so obviously for that relief we think of the Andes.
The scientists methodically examine the ground looking for fossils. Tiny clues hidden in the ground which could provide a detailed account of the history of the Amazon basin.
Here, in fact, we have an illustration of what we're after, meaning that we come to look for fossils, but these fossils have a particular interest, which is to gain a better understanding of the Amazonian ecosystem under the influence of the environment, and in particular, this environment which is linked to the Andes and the Andean tectonics.
Experts have known for a long time that the history of the Amazon forest is closely linked to that of the Andes Mountains.
It's a lower tooth.
Wow, it's spectacular.
During the growth of the mountain range, the basin was on several occasions filled with vast stretches of water, the last of which appeared about 12 million years ago. The scientists call it the Pebas Sea. Until recently, the scientific community hotly debated a key question. Was it an inland saltwater sea or a freshwater lake?
So, do you know what that is?
Yes, of course. They're oysters.
Oysters.
But sea oysters, right?
Yes, of course. And last year, we took sediment samples here, and there were foraminifera, thousands of them, thousands of foraminifera.
I've never seen oysters here before.
So we're talking about an outcrop which is extremely unusual in the Amazonian context, because it's the only outcrop that has ostrea, or oysters, throughout Amazonia. Obviously, they are fossilized oysters, marine oysters, so they resemble the oysters we eat today. They have the particularity of having been perforated by organisms, which we call lithophagous organisms, which are marine creatures. This informs us directly that 12 million years ago, or in the past in any case, there was a sea here. In fact, these oysters represent the final obstacle for the opponents of the Pebas Sea theory, who considered that this was a lake with fresh water, quite simply because no one had ever found oysters in the Pebas system. But here we are. There are.
The whole of what is today the Amazon basin was therefore covered by a vast inland sea some 12 million years ago. The appearance of the Pebas Sea in the middle of the South American continent is the result of plate tectonics. It is directly linked to the uplift of the Andes Mountains.
Through the effects of Andean tectonics, the Andes rose up about 15 million years ago. What we call the foreland, the zone that precedes the tectonized zone, the subduction zone, underwent flexure or folding and moved downwards and in doing so, it allowed the sea to move in, an ingression of the sea. This Pays-Basses Sea then gradually withdrew, and the whole biodiversity of the Pays-Basses, with hundreds of species of mollusks and marine rays, and notably a whole bunch of crocodiles, which depended on that system, all these organisms would have disappeared at the same time as the system in which they lived. On the other hand, what's certain is that the disappearance of that very particular system enabled the current Amazonian system to be established.
Through its disappearance, the Pays-Basses Sea led to the extinction of thousands of animal species. But it gave way to the most powerful river in the world. An evolution that furthered the emergence of an incomparable biodiversity.
The luxuriance, the vast biodiversity of Amazonia, in fact, is ultimately very young. It's very recent in terms of what we know today. But it's not so surprising because that host of species was born out of tectonics, from the consequences of Andean tectonics, which over millions of years led to the separation of smaller basins, of the Amazon basin and lesser basins. And all those zones were separated slightly. They have slightly different vegetation and slightly different climates, and so all that led to distinctions among species, what we call the phenomenon of speciation. These sister species would then be either in the north or the south and would ultimately evolve independently and give us this whole biodiversity that we see today.
Amazonia bears irrefutable testimony to the bonds between the living world and geology. Unremittingly, plate tectonics shape and sculpt our planet. It gives rise to seas and oceans, to mountains and forests. 3 million years ago, another phenomenon radically changed the biological equilibrium of the South American continent. The closure of the Isthmus of Panama and the junction with North America. Isolated for some 50 million years, North America was therefore colonized by new species. Once again, the land changed shape and form, transformed by the perpetual voyage of the continents across the face of the planet Earth.